When you gaze into the night sky, your attention is likely captured by grand, majestic spiral or elliptical galaxies, each a sprawling city of stars. Yet, hidden among these titans are far smaller, almost imperceptible stellar systems. Today, I want to introduce you to these miniature worlds, known as dwarf galaxies, which we are going to explore together. These galaxies are distinct from their massive cousins in every conceivable way, from their dimensions to their stellar populations. A typical dwarf galaxy might contain anywhere from a few million to a few billion stars. To give you some perspective, our own Milky Way galaxy houses around 200 billion stars, making some dwarf galaxies over 100 times less populous and significantly less massive. Their diameters are similarly small, stretching from just a few hundred to several thousand light-years across, a stark contrast to a giant like our own, which spans more than 100,000 light-years. For many decades, these faint and compact galaxies were practically ghosts, remaining hidden from astronomers. Their inherent dimness made them almost impossible to spot, even with the most powerful telescopes of the 20th century. It was only with the arrival of modern innovations, like highly sensitive digital cameras, spectroscopic analysis, and space-based observatories, that we gained the ability to systematically find and analyze these diminutive cosmic islands. Astronomers classify dwarf galaxies into several primary categories based on their appearance and composition. The most frequently observed are dwarf ellipticals, which have a rounded or oval structure and are filled with ancient stars, containing very little of the gas and dust needed for new star birth. You will also find dwarf irregular galaxies, which lack any defined shape and often feature vigorous, ongoing star formation, while the much rarer dwarf spiral galaxies mimic their larger counterparts on a smaller scale. Among the most well-known examples is the Sagittarius dwarf galaxy, which orbits our very own Milky Way. Discovered late in the 20th century, this satellite galaxy contains roughly 300,000 stars and provides a vital look into galactic evolution. Astronomers are watching in real time as the Milky Way's immense gravity gradually tears Sagittarius apart, with its tidal forces pulling stars into long, flowing streams across the sky. Scientists theorize that dwarf galaxies are, in fact, the essential building blocks of the cosmos. This idea, known as the hierarchical assembly hypothesis, suggests that massive galaxies are not born large, but are instead formed through the continuous merger of smaller systems over cosmic time. This model neatly explains why we observe so many giant galaxies attended by a retinue of smaller satellite companions, which are destined to be consumed and assimilated into the larger structure. What makes these small galaxies particularly fascinating is their incredibly high concentration of dark matter, the mysterious, invisible substance that does not interact with light. In some cases, the mass of this dark matter can outweigh the mass of all the visible stars and gas by a factor of several tens. This unique property turns dwarf galaxies into perfect natural laboratories, allowing us to probe the nature of dark matter and put our cosmological models to the test. Dwarf galaxies also serve a critical function in our understanding of the universe's chemical history. Because they have fewer stars and a low metallicity, meaning a low concentration of elements heavier than hydrogen and helium, their chemical makeup is almost pristine. This composition is very similar to how the universe looked shortly after the Big Bang, giving you a rare window into the processes that governed early star formation and cosmic chemical enrichment. The environment of a dwarf galaxy greatly influences its fate. Many are found orbiting larger galaxies like the Milky Way, where they are relentlessly battered by gravitational tidal forces that stretch and ultimately shred them. Others, however, drift in the lonely voids of intergalactic space, offering a chance to see how a galaxy evolves without outside interference. This leads to a remarkable diversity, with some dwarfs bursting with vibrant regions of rapid starbirth, while others appear as dim, static relics composed almost exclusively of ancient stars. Our journey to understand these systems began in the middle of the 20th century, though, early on, these faint smudges were often misidentified as simple star clusters or distant nebulae. The game changed with the introduction of new astronomical tools like photoelectric methods and spectroscopy. These technologies allowed scientists to measure the internal velocities of the stars, which confirmed that these were not just loose associations, but self-contained galaxies, gravitationally bound and moving as a single entity. A major breakthrough occurred in the 1980s with the development of electronic optical devices and CCD cameras, which were sensitive enough to capture incredibly faint light and enabled astronomers to conduct systematic searches for the first time. This era led to the discovery of many satellites, like the Draco and Tucana dwarfs. Even then, finding galaxies like Sagittarius and Phoenix so close to home underscored the immense challenge of spotting these objects. The advent of space telescopes and comprehensive projects like the Sloan Digital Sky Survey at the close of the century completely transformed the field, allowing for automated searches over vast swaths of the sky and revealing dozens more of these phantom galaxies orbiting our own and other nearby galactic systems. If you look back to the 1970s, you'll find that astronomers made a peculiar observation. Stars in dwarf galaxies were moving far faster than could be explained by their visible mass. This puzzling phenomenon suggested these galaxies harbor immense quantities of invisible matter, which outweighs their luminous components by 10 or even 20 times. As modern research shows, you can see that dwarf galaxies exhibit a wide range of structures and evolutionary paths, making them key to understanding how all galaxies in the universe form and develop. Your journey into understanding these objects reveals a shift from accidental sightings of faint smudges to systematic, in-depth studies. This research has not only cataloged these tiny worlds, but has also highlighted their crucial role within the cosmic web. You can think of dwarf galaxies as windows into the early universe, as natural laboratories for studying dark matter, and as fundamental building blocks in the formation of larger galaxies, including our own Milky Way. Structurally, you might be surprised by the complexity dwarf galaxies exhibit, despite their small dimensions. They are complete systems, containing stars, gas, and dust, all held within a significant halo of what we now understand to be dark matter. In contrast to giant spiral or elliptical galaxies, dwarf galaxies can present simple spherical forms, yet they display an astonishingly rich diversity of physical traits. Dwarf elliptical galaxies, for instance, typically have a spherical or slightly stretched shape and are dominated by old stars, containing very little gas or dust. This composition means you won't see active star formation within them, giving them a quiet, dormant appearance. On the other hand, dwarf irregular galaxies present more chaotic structures, filled with both old and young stars, as well as ample gas and dust to fuel ongoing stellar creation. The stellar populations you find in dwarf galaxies are also remarkably varied. In some, ancient stars, up to 12 billion years old, nearly the age of the universe itself, are the most common. These stars have low metallicity, which means they reflect the chemical makeup of the cosmos in its infancy. In other dwarf galaxies, you can witness stars forming continuously over billions of years, resulting in brilliant young stars, blue giants, and vibrant regions of star birth. The gas within a dwarf galaxy plays a pivotal role in its life story. Dwarf elliptical galaxies are unable to form new stars because they lack significant gas reserves. Conversely, dwarf irregular galaxies can possess vast gas clouds with densities ranging from tens to hundreds of solar masses per cubic parsec. You'll find these clouds act as nurseries for new stars, generating regions of spectacular high luminosity. One of the most significant discoveries in recent decades is the sheer dominance of dark matter in dwarf galaxies. Dynamical studies confirm that stars in these systems move much faster than their visible mass should permit. In certain cases, dark matter outweighs all visible matter by a factor of 10 or more, making these galaxies indispensable for your efforts to understand the nature of dark matter and test cosmological models. The chemical makeup of stars in dwarf galaxies also offers you profound insights into the universe's earliest evolutionary stages. These small systems often preserve the original proportions of hydrogen and helium, with only minimal heavier elements, closely resembling the conditions shortly after the Big Bang. By analyzing the spectra of their stars, you allow astronomers to better comprehend the processes that created the first stellar generations. The dynamics of dwarf galaxies are just as unique. Their stars are influenced not only by their own gravity, but also by the powerful tidal forces of larger galactic neighbors. As you observe satellite galaxies like the Sagittarius or Phoenix dwarf, you can see them being gradually pulled apart by the Milky Way's gravity, forming immense stellar streams. These events allow you to watch in real time how small galaxies contribute to the structure of larger ones. Morphological variation is another of their notable features. Even within a single classification, you can observe significant differences in shape and density, from nearly perfect spheres to chaotic arrangements of stars and gas. These distinctions are shaped both by internal processes, like star formation and stellar winds, and by external forces, such as tidal interactions and mergers with other systems. In essence, the structure and composition of dwarf galaxies represent a complex interplay of physical forces, from stellar populations to dark matter. These tiny worlds not only deepen your understanding of galactic evolution, but also serve as natural laboratories for studying the universe's fundamental properties. Many of these galaxies, you will find, are located near giant systems like our Milky Way or Andromeda. In the next chapter, we will examine dwarf galaxies as satellites of larger systems, exploring their orbital paths, tidal interactions, and their profound impact on the evolution of the Milky Way and its neighbors. You will learn how these small galaxies become the source of stellar streams and how their movements help reveal the hidden architecture of dark matter. These small cosmic worlds orbit their massive hosts, and their presence fundamentally shapes the development of large galaxies like our own. You can picture these dwarf galaxies orbiting the center of our own galaxy, with their trajectories being mapped out using modern astrophysical methods. However, their orbital paths are far from consistently stable. The immense tidal forces of the Milky Way continually stretch them, creating stellar streams that persist for billions of years. These are like glowing trails of small galaxies pulled apart by the gravity of a giant. Tidal interactions represent a fundamental mechanism that shapes the evolution of these dwarf satellites. As a smaller galaxy ventures close to a massive one, you can see the larger galaxy's gravity begin to siphon stars and gas clouds away from the satellite's less defended core. This interaction can trigger the gradual disintegration of the dwarf galaxy, meaning many of the faint systems we observe today are actually in their final stages of dissolution. And in millions of years, they will be nothing more than a stellar stream fully assimilated by the giant galaxy. Looking at the dwarf galaxies around Andromeda, such as Messier 32 and Messier 110, also reveals the impact of these tidal effects. These systems demonstrate that the capture and dismantlement of small galaxies is a universal process throughout the cosmos. Such interactions not only sculpt the structure of stellar streams, but are also a primary means for large galaxies to grow by accumulating new stars and gas. The dynamic behavior of satellite dwarf galaxies also gives us a powerful method for studying the distribution of dark matter. Based on the laws of gravity, the speed of stars within a dwarf galaxy is influenced not only by visible mass, but also by the presence of this invisible material. By measuring their orbital movements and tidal stretching, astronomers like me can create maps of dark matter's distribution in large galaxies, a feat that is impossible to accomplish through direct observation. What I find especially compelling is that dwarf satellite galaxies do not always maintain stable orbits. In some instances, they might be captured and subsequently ejected from the system, following a close interaction with another dwarf galaxy or their massive neighbor. These events produce unique arrangements of stellar streams, which allow us to trace the history of galactic encounters over billions of years. Beyond their gravitational effects, dwarf satellite galaxies also influence the chemical composition of the giants they orbit. As a satellite is torn apart, its stars and gas mix into the matter of the larger galaxy, introducing new elements, including metals that were produced during star formation. This enrichment process plays a critical role in defining subsequent stellar generations within massive galaxies and propels the system's overall chemical evolution. Of course, there are also isolated dwarf galaxies that are not gravitationally tied to any large neighbors. Studying these systems helps us understand how small galaxies evolve on their own, free from tidal interference. These galaxies frequently display very low metallicity, which suggests they hold on to chemical conditions akin to those of the early universe. They serve as essential reference points for examining the initial phases of galaxy formation and the processes that defined the young cosmos. Particularly fascinating are the observations of dwarf galaxies at the very limit of our detection capabilities. For example, faint satellites of the Milky Way with extremely low surface brightness were only discovered thanks to deep, wide-field surveys and advanced CCD cameras. These discoveries suggest to me that the total population of dwarf satellites may be much larger than previously assumed, revealing a dynamic picture that is incredibly complex and varied. So, as you can see, dwarf satellite galaxies fulfill a dual role. They are victims of tidal forces that transform them into stellar streams, and they are also donors of new stars and gas to their larger hosts. Studying them not only unveils the dynamics and chemical evolution of giant systems, but also provides deep insights into the distribution of dark matter and the complete history of galaxy formation. The process of how dwarf galaxies form began in the nascent universe, shortly after the Big Bang, when the first dense regions of gas and dark matter started to take shape. These small concentrations of matter were the seeds from which future dwarf galaxies would grow. In contrast to giant systems that arose from numerous mergers and the accretion of material, dwarf galaxies tended to develop in relative isolation, which left them more vulnerable to local conditions and external forces. In the first millions of years of cosmic history, primordial gas, consisting almost entirely of hydrogen and helium, started to collapse under its own gravity. Within these collapsing clouds, the first protostars were born, which evolved over millions of years to become the cores of dwarf galaxies. Many modern dwarf galaxies still contain traces of this primitive gas, identified by its low metallicity and minimal content of heavy elements, making them unique relics of that early cosmic epoch. Throughout their formation, dwarf galaxies were also subject to internal forces. Supernovae from the first generations of stars blasted enormous amounts of energy and particles into space, creating powerful stellar winds and disrupting local gas dynamics. In the confines of small dwarf systems, these events could lead to a partial loss of gas, which would in turn slow down star formation and introduce chemical irregularities within the galaxy. In addition to these internal processes, you have to consider the critical impact of external influences. Dwarf galaxies situated near giant systems feel tidal forces that can reshape their structure and form. Even comparatively minor interactions could stretch out stars and gas, creating long stellar streams and triggering new star-forming regions in unstable areas. In some scenarios, tidal effects could lead to the total annihilation of a dwarf galaxy, leaving behind only scattered star clouds in the gravitational field of the larger system. Modern observations indicate that dwarf galaxies arise not only from primordial gas clouds, but also through the consolidation of smaller structures. For instance, 2 or 3 small gas systems can merge to produce a medium-sized dwarf galaxy. This mechanism, which we call hierarchical formation, is a key component of the lambda cold dark matter or lambda CDM cosmological model, as it explains the growth of galaxies and the formation of large-scale structures in the universe. Ultimately, the chemical signature of a dwarf galaxy tells the story of its origin. Its composition reflects its unique formation history, from the specific elements it contains to their abundance, offering us a direct link to the conditions that prevailed in the very young cosmos. When you examine ancient systems, you find they are dominated by stars with low metallicity, composed almost entirely of hydrogen and helium. Younger dwarf galaxies, by contrast, present a mixture of old and new stellar populations, alongside active regions of star formation. It is in these cosmic nurseries that intense star creation forges subsequent generations, enriching them with heavy elements such as carbon, oxygen, and iron. The very formation of dwarf galaxies is also deeply connected to the role of dark matter. The gravitational field generated by this invisible substance is what holds the gas and stars within the galaxy, preventing their escape into the void of intergalactic space. You can observe the influence of dark matter most clearly in these small systems. Without its presence, dwarf galaxies would have been incapable of maintaining their structure and evolving over billions of years. A fascinating aspect of their development is the impact of radiation from the universe's first massive stars and quasars. The powerful energy and photon flux from these objects could heat the gas in dwarf galaxies, which would stop it from cooling, and thereby slow down the process of star formation. This demonstrates how external sources of light and energy, even from hundreds of thousands of light-years away, significantly shaped the evolution of small galaxies. You should also note that dwarf galaxies that formed in isolation can vary dramatically in their structure and composition, compared to those that grew near giant systems. An isolated dwarf galaxy often presents a simple spherical or mildly irregular shape, with low metallicity and scarce gas. In stark contrast, the satellite galaxies orbiting large systems show signs of complex interactions, tidal effects, and much greater diversity in their chemical makeup. The formation of dwarf galaxies is therefore the outcome of a complex interplay between internal and external forces. These range from the gravitational collapse of primordial gas and the initial bursts of star creation, to tidal interactions with neighbors, and the foundational influence of dark matter. It is these processes that produce the incredible variety of small galaxies you see in the modern universe, offering scientists a window into the early stages of galactic evolution and cosmic history. Star formation in dwarf galaxies is a unique process, highly dependent on the mass, chemical composition, and environment of each system. Rather than the continuous large-scale star production seen in massive galaxies, star birth in dwarf galaxies happens erratically, marked by active periods, followed by long phases of dormancy. It's important for you to realize that despite their modest size, these galaxies can generate stars both in isolated bursts and in dense clusters, forming small stellar systems that eventually integrate into the galaxy's overall structure. The fundamental raw material for creating stars is cold molecular gas. However, its concentration within dwarf galaxies is often quite low, a consequence of the system's small mass and external pressures like tidal forces and radiation from nearby galaxies. Without a sufficient supply of this gas, the intensity of star formation plummets, and the galaxy may enter a quiescent state that can last for billions of years. Chemical composition is another critical factor in this equation. The primordial dwarf galaxies that emerged in the early universe possessed extremely low metallicity. In such conditions, gas cools much more slowly, making the star formation process less efficient. Over time, as supernovae from the first generation of stars ejected heavy elements into the cosmos, new generations of stars were able to form more rapidly and effectively, building a more complex galactic architecture. Supernovae and stellar winds actually have a dual impact. On one hand, they infuse the surrounding gas with new chemical elements, setting the stage for the next wave of stars. On the other hand, the violent expulsion of energy and matter can disperse the gas, lowering its density in crucial regions and temporarily bringing star formation to a halt. In dwarf galaxies, you can see the effects of these events with particular clarity. A single brilliant supernova can expel a large fraction of the galaxy's gas, profoundly changing its dynamics. Tidal interactions with large neighboring galaxies also shape the star formation process. As a dwarf galaxy draws closer to a giant, gravitational forces might either compress the gas at its core to trigger star birth, or they could strip the gas away, preventing new stars from forming. Consequently, a satellite's orbital path and position around a large galaxy become decisive factors in its history of stellar creation. Observations reveal that actively forming dwarf galaxies often contain small, dense star clusters at their core or along gas clouds, while dormant ones have more uniformly distributed stars and are nearly devoid of gas. Astronomers pay special attention to dwarf galaxies located on the periphery of large clusters. In these environments, intense X-ray and ultraviolet radiation from neighboring galaxies can heat the gas, preventing it from cooling and effectively suppressing star formation. In the most extreme instances, these processes result in what are known as quasi-dead dwarf galaxies, where virtually no new stars have been born for billions of years. Modern observations with space telescopes like Hubble and the James Webb Space Telescope enable us to study star formation even in the most faint dwarf galaxies. These powerful instruments can resolve individual star clusters, analyze the spectral properties of gas, and ascertain the ages of different stellar populations. This wealth of data helps scientists construct detailed models of how small galaxies evolve and allows them to forecast their future development. Finally, star formation in dwarf galaxies is inextricably linked to dark matter. The gravitational field it creates is essential for retaining gas and preventing its dispersal. Without a sufficient concentration of dark matter, gas clouds would readily escape the weak gravity of a small galaxy, thereby terminating the process of new star creation. This shows how, even on these small scales, dark matter plays an indispensable role in maintaining a galaxy's structure and activity. In essence, dwarf galaxies display a remarkable diversity in their star-forming processes. They can be vibrant workshops with numerous star clusters and bright gas accumulations, or they can be quiet relics where new stars are a rarity. The evolution of any galaxy is shaped by a combination of factors, including its own internal properties, the powerful influence of supernova winds, and external pressures like the tidal forces and radiation from its cosmic neighbors. When you look at dwarf galaxies, you find an incredibly varied collection of small stellar systems that differ in their form, internal structure, chemical makeup, and the intensity of their star formation. Despite their small stature, they are absolutely crucial for understanding the universe's development, serving as invaluable living laboratories where we can witness processes that were common in the early cosmos. To make sense of this diversity, astronomers like myself typically categorize dwarf galaxies into a few primary classifications. You have the dwarf spheroidal, the dwarf irregular, and the dwarf elliptical types. Each of these categories possesses a unique set of traits that dictates its evolutionary journey and its capacity for creating new stars. This framework helps us understand the distinct paths these small galaxies can take through cosmic history. Let's start with dwarf spheroidal galaxies, which are the kind you'll most commonly find orbiting large systems like our own Milky Way or the Andromeda Galaxy. These are characterized by a rounded form, very low surface brightness, and a near total absence of gas, rendering them dormant systems with virtually no new star birth. Their stellar populations are spread out quite evenly, and their low metallicity, a low concentration of elements heavier than hydrogen and helium, signals their ancient origins, suggesting most of their stars were formed in the universe's earliest epochs. In stark contrast, you have dwarf irregular galaxies, which are distinguished by a much more chaotic arrangement and often hold significant reservoirs of gas. These systems can be vibrant hubs of star formation, particularly within their cores or inside dense gas clouds. Their jumbled appearance is a product of both internal dynamics, such as gravitational instabilities and stellar winds, and powerful external influences, like the gravitational pull from more massive galactic neighbors. Sitting between these two extremes are the dwarf elliptical galaxies, which I see as an intermediate classification. They exhibit an elliptical profile, a moderate amount of gas, and a level of star-forming activity that, while low, has not ceased entirely. You often find these galaxies within clusters or as companions to larger systems, where tidal forces and radiation from their neighbors progressively alter their structure, stripping away gas and gradually shutting down the creation of new stars. This variety among dwarf galaxy types is also clearly reflected in their chemical fingerprints. Spheroidal and elliptical systems generally show low metallicity, which tells you that subsequent generations of stars have done very little to enrich their gaseous medium. Conversely, in dwarf irregulars, you can see much greater variation, with some being ancient, almost pristine systems, and others being relatively young, with ongoing starbirth actively seeding the surrounding gas with heavy elements. Ultimately, the size and mass of a dwarf galaxy are direct drivers of its fate. The smallest galaxies are far more susceptible to external disruptions, such as tidal stripping and radiation from nearby giants, which can bring their star formation to a complete stop. Larger dwarfs, however, can leverage their stronger gravitational fields to hold on to their gas reserves and continue producing stars for billions of years, even if it's on a much smaller scale than in giant galaxies like ours. It's also important to understand that dwarf galaxies frequently exist as satellites orbiting more massive systems, and their arrangement around these giants is anything but random. Tidal interactions sculpt their orbits and internal structures, profoundly affecting their dynamics. These gravitational encounters can either spark intense bursts of star formation, or, conversely, strip away their gas, forcing the entire system into a quiescent state. These interactions show you the continuous dynamic relationship that exists between large and small galaxies, where each profoundly influences the other's evolution. Interestingly, our observations have uncovered some truly unusual dwarf galaxies that don't fit neatly into these standard boxes. For instance, you can find systems with active star-forming regions that somehow maintain a nearly spheroidal shape, or irregular galaxies that are temporarily devoid of gas. These transitional examples provide compelling evidence that the evolution of a dwarf galaxy is an intricate, multi-stage journey, determined by numerous variables, from its internal mass and gas supply to its interactions with neighbors and the influence of dark matter. As a result, the contemporary view of dwarf galaxies reveals an immense spectrum of possibilities, from ancient, dormant, spheroidal systems to dynamic, gas-rich irregulars. Every one of these systems tells a unique story, written in the layout of its stars and its specific chemical makeup, which allows scientists to reconstruct the processes of cosmic formation and evolution. Despite their compact dimensions, these galaxies have a complex architecture that includes stars, gas clouds, and dark matter. And by studying these components, we can better understand how they maintain their integrity and evolve over billions of years. The most visible component of a dwarf galaxy is, of course, its stars. In spheroidal systems, you'll see that the stars are distributed with relative uniformity, creating an almost symmetrical core and a faint outer halo. In their irregular counterparts, stars are often found bunched together in clusters, or dense pockets where starbirth has happened recently, or is still underway. Dwarf ellipticals present a middle ground, with stars that are more concentrated toward the center, but which disperse gradually toward the edges, creating a smoother profile of light. However, what truly ensures the dynamic stability of these small galaxies is the gravitational grip of dark matter. Despite their low visible mass, you'll find that dwarf galaxies are typically embedded within a massive halo of this invisible substance. This dark matter halo provides the gravitational scaffolding that holds stars and gas together, preventing them from flying apart and establishing a stable gravitational field. Without this unseen support, these systems would be easily torn to shreds by tidal forces from larger neighbors or by their own internal processes. Finally, the gaseous components within dwarf galaxies play a significant role in shaping their structure and dynamics. The amount of gas, where it's located, and how it moves are all critical factors that determine whether a galaxy can form new stars. This gas is the raw fuel for stellar nurseries, and its interaction with stars, supernovae, and the surrounding cosmic environment dictates the long-term evolutionary path of the entire system. In dwarf irregular galaxies, you find that gas is gathered into distinct clouds or bands, where its density becomes high enough to trigger star formation. Conversely, in spheroidal and elliptical systems, the gas is often entirely missing, or exists only as a tenuous, widespread shell. The distribution of this gas is highly inconsistent and susceptible to external pressures. Factors like ultraviolet radiation from nearby galaxies, tidal forces, and encounters with intergalactic matter can shift, compress, or even strip these gas clouds away entirely. The internal mechanics of dwarf galaxies hinge on a delicate equilibrium between gravity, the pressure exerted by gas, and the kinetic energy of the stars. Within spheroidal dwarf galaxies, stellar movements are primarily random and chaotic, showing very little organized rotation. In irregular systems, however, you can observe clear elements of rotation and orderly motion among both gas and star clusters, while dwarf elliptical galaxies feature a blend of both chaotic and structured dynamics, positioning them as transitional forms from an evolutionary perspective. You can see that many dwarf galaxies bear the telltale signs of interacting with their neighbors, such as elongated tails of stars, imbalanced gas distributions, and distortions in their overall shape. These characteristics point to a history of tidal encounters, the capture of gas, and even partial mergers with other small galaxies. By analyzing these features, astronomers can piece together the histories of these interactions and better grasp the part dwarf systems play in the assembly of larger galaxies. The energy balance inside dwarf galaxies is actively regulated by supernova winds, blowing from massive stars, and the turbulence of interstellar gas. These processes not only control the rate of star formation, but also stop gas clouds from collapsing too much, which helps preserve the galaxy's structural integrity. However, if the energy from these ejections becomes strong enough to overcome the galaxy's gravitational pull, some gas can escape, leading to a temporary or even permanent shutdown of new star creation. Of particular interest is the orbital behavior of dwarf satellites as they circle giant galaxies. Their paths are governed by the laws of tidal dynamics, where even slight perturbations can rearrange their gas and stellar makeup. Orbits that bring a dwarf galaxy close to the core of its massive neighbor frequently result in the stripping of its gas, transforming it into a dormant spheroidal system. In contrast, dwarf galaxies on more distant orbits can maintain active star formation, though it often occurs in periodic bursts. The observations provided by space telescopes like Hubble and James Webb have given scientists an unprecedented ability to examine the internal structure and dynamics of dwarf galaxies. We've been able to identify individual stellar populations, map gas clouds in great detail, and pinpoint the subtle traces of past interactions. This wealth of data is crucial for modeling the evolution of small galaxies, forecasting their future development, and clarifying their role in the formation story of large-scale cosmic structures. Ultimately, the structure and dynamics of dwarf galaxies emerge from a complex web of interconnected forces. The arrangement of stars, the concentration of gas, the unseen influence of dark matter, internal energy processes, and external interactions all combine to dictate a galaxy's stability, its capacity to form new stars, and its evolutionary path over cosmic timescales. Although dark matter doesn't emit light or directly engage with ordinary matter, its gravitational pull is one of the most fundamental forces shaping the universe, dictating the structure and motion within dwarf galaxies. Examining dark matter in these small galaxies offers you a unique window into understanding how this invisible mass influences stars, gas, and the overall development of these systems. Dwarf galaxies possess a relatively low amount of visible mass, which makes them especially sensitive to gravitational forces. Without a substantial amount of dark matter, these tiny systems would be incredibly fragile, as internal events like stellar winds and supernova explosions, or external forces like tidal pulls from larger neighbors, could easily cause their stars and gas clouds to disperse. Modern observations confirm that dwarf galaxies are enveloped by immense halos of dark matter, which can outweigh their visible matter by tens or even hundreds of times. This halo generates a powerful gravitational well that effectively holds stars and gas within the galaxy's confines. By studying rotation curves and the distribution of stars, astronomers are able to map out how dark matter is arranged in these systems, typically finding it is densest at the center and becomes more diffuse toward the edges. The significance of dark matter becomes especially clear when you look at dwarf spheroidal galaxies, which have almost no gas or active star formation. In these systems, the observable mass of the stars is far too low to account for the gravitational cohesion that keeps the galaxy intact. The existence of a massive dark matter halo is the only viable explanation for how these dormant systems can persist for billions of years while maintaining their compact and stable form. Dwarf irregular galaxies are similarly governed by the influence of dark matter, though in their case, its effects are intertwined with gas dynamics and active star-forming processes. The gravitational field produced by dark matter stabilizes the movement of gas clouds, preventing them from scattering and creating the necessary conditions for new stars to be born. Without this gravitational scaffolding, these galaxies would rapidly lose their gas, causing their star-forming activity to plummet. The impact of dark matter is also apparent when dwarf galaxies interact with their neighbors. Tidal forces that arise from proximity to a large galaxy can stretch and deform the stellar and gaseous components. The massive dark matter halo, however, can absorb a portion of these disruptions, acting as a gravitational shield that helps prevent the galaxy's complete destruction and ensures its survival. Modeling confirms that systems with substantial dark matter can maintain their structure and activity over long periods, even after repeated encounters. Furthermore, the gravitational field of dark matter directly influences how stellar populations are arranged within the galaxy. This often results in a distinct gradient, where older stars tend to congregate in the central region, while younger stars are more likely to form on the periphery. This separation creates noticeable gradients in both the age and the metallicity of the stars across the galaxy. What's truly compelling is that the study of dwarf galaxies allows us to put various theories about dark matter to the test. By analyzing their rotation curves, mass, and stellar arrangements, scientists can define the properties of dark matter, including its density, its interaction with conventional matter, and the architecture of its halo. These findings are essential not just for grasping the evolution of small galaxies, but also for assembling a comprehensive picture of the universe. Dark matter's effect on dwarf galaxies is also apparent in their long-term development. The surrounding halo lends stability against cosmic disturbances, reduces the loss of gas, and preserves a dynamic balance. Consequently, dwarf galaxies can endure for billions of years, effectively becoming living laboratories, where you can study the processes that took place in the early cosmos, as the first stars and galaxies were forming. Therefore, dark matter serves as the invisible but absolutely vital foundation for dwarf galaxies. It is the reason for their existence, enabling them to hold on to their stars and gas, stabilizing their forms, and allowing us to observe the processes of starbirth in these small systems. In the absence of dark matter, dwarf galaxies would be fleeting and unstable phenomena, stripped of their unique scientific potential. Our grasp of dwarf galaxies is a relatively recent development when compared to the study of gigantic spiral and elliptical galaxies. The very first indications of these small systems came about in the middle of the 20th century, when astronomers started to detect indistinct, faint objects orbiting the large galaxies within our own local group. These objects were mere ghosts on photographic plates and early sky surveys, and it took significant technological progress to finally confirm their identity as independent systems. The Ursa Major dwarf galaxy stands out as one of the first dwarf companions to the Milky Way ever identified, and it remains one of our galaxy's closest neighbors. Its incredibly low luminosity and scattered star population made it a significant challenge to observe. Critically, this discovery underscored the urgent need for more meticulous observations of faint cosmic objects, and spurred advancements in the techniques of photometry and spectroscopy for these smaller galaxies. As time went on, additional discoveries, such as the Ursa Minor, Sculptor, and Fornax dwarf galaxies, solidified a new understanding among astronomers. It became clear that these small galaxies were not rare outliers, but were actually a widespread feature of the cosmos. It turns out that most large galaxies are accompanied by a retinue of satellites, sometimes numbering in the dozens or even hundreds of dwarf systems. The advent of orbiting observatories, most notably the Hubble Space Telescope, was a turning point in this field of research. With the exceptional sensitivity and sharp resolution of modern instruments, we could finally spot faint objects far across space, precisely measuring their dimensions, forms, and stellar makeups. Observations from Hubble revealed that dwarf galaxies are remarkably varied in their structure, chemical makeup, and the intensity of their star formation. Contemporary projects like the Sloan Digital Sky Survey, or SDSS, and other major spectroscopic initiatives have dramatically enlarged the known catalog of dwarf galaxies. They have uncovered a multitude of tiny systems orbiting not just Andromeda, but also more remote galaxies, validating the theory that dwarf galaxies are a fundamental building block of the universe's structure. Beyond simply finding new objects, these surveys have also helped us map satellite orbits and chart the layout of gas and stars. The story of how we found dwarf galaxies is inseparable from the advancement of our observational tools. The initial photographic plates and early telescopes had limited capabilities, revealing only the closest of these objects. It was the introduction of charge-coupled device, or CCD cameras, and digital sensors that brought a huge leap in sensitivity, allowing us to find faint systems with very low surface brightness. It's worth noting that the first sightings of dwarf galaxies were often greeted with doubt. Initially, many considered them to be nothing more than indistinct patches within the outer halos of larger galaxies. It was only through the gradual buildup of data on their star distribution, chemical profiles, and internal dynamics that we could definitively establish them as self-contained galaxies, complete with their own gravitational pull and unique evolutionary path. Research into dwarf galaxies today is an active field, relying on information from both Earth-based and spacefaring telescopes, complemented by sophisticated computer modeling. Astronomers are currently exploring their dynamic relationships with larger galaxies, the influence of dark matter, the mechanisms of starbirth, and the processes of chemical enrichment within them. The history of finding these tiny systems shows how the steady enhancement of our observational tools lets us reveal ever more intricate and faint objects, deepening our knowledge of the cosmos. Ultimately, the chronicle of discovering dwarf galaxies is a narrative of improving astronomical technology, of slowly coming to accept the existence of these faint systems, and of appreciating their profound importance in the story of galactic evolution. Every new finding brings us one step closer to comprehending how the structures in the local group, and indeed on the grandest cosmic scales, were formed and developed over time. Today's astronomy is equipped with an extensive toolkit for investigating dwarf galaxies. Even though they are small and dim, modern telescopes and advanced data processing techniques enable us to scrutinize their structure, stellar makeup, and movements in great detail. These technologies are forging new paths toward understanding these small galaxies, their place in the universe's evolution, and their interactions with larger galaxies. One of the cornerstone techniques for finding them is deep photometry, a method that uses extremely sensitive imaging to detect objects that exhibit very low surface brightness. To find faint dwarf galaxies against the vast backdrop of the sky, you can use a combination of charge-coupled device, or CCD, cameras, digital detectors, and long exposure times. This approach allows you to resolve individual stars and analyze how luminosity is distributed across the galaxy. These techniques have now become the standard in the field, making it possible to uncover celestial objects that were once completely hidden from view. Modern astronomical projects like the Sloan Digital Sky Survey, also known as SDSS, Pan-STARRS, and the Dark Energy Survey, or DES, are designed to methodically discover dwarf galaxies both within our local group and far beyond it. These ambitious surveys map enormous sections of the sky, gathering extensive photometric and spectroscopic data. By applying automated algorithms to this information, you can efficiently detect faint objects and filter out background noise, which helps in discovering new dwarf galaxies and better defining their characteristics. Spectroscopy serves as an essential instrument for verifying the physical identity of any object you find. This technique enables astronomers to gauge stellar velocities, assess chemical makeup, and map the distribution of metallicity. Such parameters are critical for distinguishing a true dwarf galaxy from a star cluster or another type of celestial body, while also providing deep insights into its internal motion and evolutionary history. Today's spectroscopic tools offer remarkable precision and sensitivity, allowing for data collection from even the most dim and distant objects. Astrometric data, like the kind gathered by the Gaia Space Observatory, provides exceptionally precise measurements of the coordinates and movements of stars inside dwarf galaxies. This information is invaluable for determining the orbital paths of satellite galaxies as they circle larger systems, for spotting the telltale signs of tidal interactions, and for constructing models of how dark matter is distributed. The level of accuracy Gaia provides has revolutionized the study of the structure and dynamics of these small galaxies. When you want to detect dwarf galaxies situated well beyond our own local group, a more complex strategy is required. This often involves combining data from multiple telescopes using very long exposures, along with observations from space-based instruments in the infrared and ultraviolet spectrums. Infrared telescopes can peer through clouds of dust to reveal faint galaxies, while ultraviolet observations can pinpoint areas where star formation is actively occurring, giving you a much more holistic view of these systems. Computer simulations and machine learning are also playing an increasingly vital role in this field of study. Sophisticated algorithms are now used to sift through immense data sets, helping you to isolate subtle objects from the background noise and systematically analyze their features. Furthermore, models that simulate the dynamics and evolution of dwarf galaxies allow you to better interpret observational data, predict the behavior of gas and stars, and test theories about the influence of dark matter. Occasionally, you can discover dwarf galaxies by observing their direct interactions with much larger ones. Clues such as elongated tails of stars and gas, asymmetrical patterns in brightness, or other visible signs of tidal disruption often point to the existence of a faint satellite that would otherwise be nearly impossible to see. Studying these interactions provides a unique window into the mechanics of tidal evolution and the part that dwarf galaxies play in building up massive galactic systems. As you can see, the methods for finding and analyzing dwarf galaxies are in a state of constant advancement. The ongoing development of larger telescopes, more advanced space observatories, better digital detectors, and smarter computational algorithms allows for the detection of objects with even lower surface brightness. This progress enables you to determine their dynamic properties with greater precision and to create more detailed maps of dark matter distribution, ultimately enriching our understanding of the universe. Dwarf galaxies display a remarkable variety in their structure, composition, and levels of activity. Despite their diminutive size, these systems are categorized into several distinct types, each possessing its own unique set of characteristics. This classification system helps astronomers to bring order to their observations, investigate the evolutionary paths of these small galaxies, and understand their complex interactions with larger galactic neighbors. Dwarf galaxies display a remarkable variety in their structure, composition, and levels of activity. Despite their diminutive size, these systems are categorized into several distinct types, each possessing its own unique set of characteristics. This classification system helps astronomers to bring order to their observations, investigate the evolutionary paths of these small galaxies, and understand their complex interactions with larger galactic neighbors. Dwarf galaxies display a remarkable variety in their structure, composition, and levels of activity. Despite their diminutive size, these systems are categorized into several distinct types, each possessing its own unique set of characteristics. This classification system helps astronomers to bring order to their observations, investigate the evolutionary paths of these small galaxies, and understand their complex interactions with larger galactic neighbors. One of the principal categories is the dwarf spheroidal galaxy, or DSPH. These systems are characterized by their nearly spherical shape, a scarcity of gas, and extremely low rates of star formation. The stars they contain are typically very old and have low metallicity, which suggests they formed early in the universe's history and have long since ceased creating new stars. You often find dwarf spheroidals as satellites orbiting larger galaxies like our own Milky Way and Andromeda, making them key subjects for studying dark matter. Another significant category is the dwarf irregular galaxy, known as DIRR. These galaxies are defined by their chaotic, asymmetrical forms, their substantial reserves of gas, and their ongoing, active star formation. You can find them both orbiting larger galaxies and existing in isolation, where the absence of strong gravitational forces allows them to hold on to their gas and continue producing new generations of stars. For this reason, dwarf irregulars are often used as natural laboratories for studying star formation in unique environments. Finally, you have dwarf elliptical galaxies, or DE, which essentially look like scaled-down versions of massive elliptical galaxies. They possess a dense spherical structure, contain very little gas, and are populated by old stars. These are commonly found within galaxy clusters, where interactions with neighboring galaxies and tidal forces have stripped away their gas, halting any new star formation. A fascinating related class is the low surface brightness, or LSB galaxy, which is exceptionally difficult to spot because its light is spread out so thinly that it barely stands out from the night sky. By examining these small systems, you can probe the effects of dark matter and environmental forces on galactic dynamics. The physical form of a dwarf galaxy is intimately connected to its evolutionary path and its interactions with larger galaxies. For instance, powerful tidal forces can stretch out the stellar components of a dwarf irregular galaxy and strip away its gas, transforming it into a spheroidal type, whereas a galaxy in isolation can hold on to its gas reserves and continue forming stars for billions of years. The classification scheme for dwarf galaxies also takes into account their chemical makeup and the age of their stars. Systems with old, low metallicity stellar populations, such as dwarf spheroidal, or DSPH, and dwarf elliptical, or DE galaxies, offer a window into the earliest phases of galaxy formation. In contrast, dwarf irregular galaxies, known as DIRR, reveal more intricate chemical histories and are still actively creating new generations of stars. Contemporary observations confirm that the majority of large galaxies, including our own Milky Way, are encircled by a retinue of dwarf satellites of various types. The Milky Way, for example, hosts both spheroidal companions filled with ancient stars and several irregular dwarfs experiencing vibrant star formation. This variety points to a complex history of mergers, tidal stripping, and other interactions that have sculpted these smaller galaxies over cosmic time. Organizing dwarf galaxies into distinct categories is therefore fundamental to comprehending their evolution and their broader significance in the cosmos. This process allows astronomers to connect a galaxy's physical and chemical traits with its dynamic processes, gauge the influence of dark matter, and dissect the mechanisms of star formation. A clear understanding of these types helps construct accurate models of the local group and more distant galactic structures, uncovering the principles that govern the architecture and development of these small systems. Despite their small stature and faintness, dwarf galaxies harbor a remarkable diversity of stellar populations, each serving as a chronicle of the galaxy's life. In dwarf spheroidal galaxies, the stars are predominantly ancient and poor in metals. This indicates that star formation in these systems ceased billions of years ago, with virtually no new stars being born since. Their low metallicity, meaning a low concentration of elements heavier than helium, mirrors the conditions of the early universe, allowing astronomers to piece together the history of cosmic chemical enrichment. Dwarf irregular galaxies present an entirely different stellar profile. Within them, you can find both ancient stars and young ones, alongside clusters where new stars are actively being born. The abundant gas in these galaxies fuels a continuous cycle of star formation that has lasted for billions of years, with each successive generation enriching the system with heavier elements. Observing these galaxies provides a direct look into the processes of stellar birth and the dynamic influence of dark matter on small galactic systems. Special consideration is given to dwarf elliptical galaxies, which are characterized by a dominance of old stars. These galaxies are frequently located within galactic clusters, where a clear pattern emerges. The denser the surrounding environment, the fewer young stars and gas reserves the galaxy contains. The stellar history of these systems strongly suggests that interactions with neighbors, tidal forces, and processes that compress and expel gas play a decisive role in their evolutionary journey. The methods used to investigate these stellar populations include photometric and spectroscopic observations, complemented by astrometric data. Photometry is used to determine the age and color of stars, enabling the construction of Hertzsprung-Russell diagrams for the entire galaxy, and revealing the sequence in which different generations formed. Meanwhile, spectroscopy yields precise information on chemical composition, and astrometry tracks the movements of stars, uncovering key details about a galaxy's structure and dynamics. A fascinating characteristic of dwarf galaxies is the existence of multiple stellar generations, which can sometimes exhibit significant differences in age and metallicity. In certain dwarf galaxies, like some satellites of Andromeda and the Milky Way, astronomers find remnants of young stellar populations even within systems that are overwhelmingly old. This points to periodic episodes of star formation, likely ignited by interactions with other galaxies or tidal disturbances. Dwarf galaxies also serve as essential laboratories for investigating the effects of dark matter. The dynamics of stars, especially within DSPH galaxies, indicate that the total mass of these systems far surpasses the mass of all their visible components combined. This observation confirms that dwarf galaxies are among the most dark matter-dominated objects in the universe, helping scientists to refine models of how dark matter is distributed on smaller scales. By observing these stellar populations, astronomers can reconstruct the complete evolutionary timeline of a dwarf galaxy. Its origin and early history are revealed by old stars, while its current state and future path are indicated by young stars. Each population acts as evidence of its evolutionary journey, chemical enrichment, and star formation processes, making dwarf galaxies invaluable objects for understanding the cosmos as a whole. Dwarf galaxies seldom exist in complete isolation. They are more commonly found as satellites orbiting large galaxies like the Milky Way or Andromeda. Consequently, their evolution is inextricably linked to the influence of these more massive neighbors. The gravitational pull exerted by the larger galaxy is one of the most critical factors in this relationship, dictating the orbits of the dwarf galaxies and fundamentally shaping their structure, stellar populations, and gas content. Satellite galaxies can trace orbits that are either nearly circular or highly stretched, causing them to periodically draw closer to and then move away from their host galaxy. Every time a satellite makes a close pass, it endures powerful tidal forces that can warp its shape, stretch out its stars and gas, and pull material into long streamers known as tidal tails. These phenomena are especially pronounced in dwarf spheroidal and elliptical galaxies, where such gravitational tides can completely reshape the distribution of their stellar and gaseous components. The Milky Way's own satellite galaxies offer clear examples of these gravitational struggles. Both the Sagittarius dwarf galaxy and the Large Magellanic Cloud show distinct evidence of being influenced by tides, visible in their elongated shapes and the streams of stars they have left in their wake. By studying these features, Astronomers can piece together the orbital past of these galaxies, gauge the intensity of the gravitational pull they experience, and develop sophisticated models of their tidal evolution. Tidal forces are a primary driver behind the transformation of dwarf galaxies. For example, a dwarf irregular galaxy, when subjected to intense gravitational strain, can eventually morph into a dwarf spheroidal system. This process strips away much of its gas and leaves behind only its older star populations, which helps to account for the wide variety of shapes we see among the satellite galaxies of larger systems, and connects their evolution to the overall dynamics of the local group. In some cases, these gravitational interactions lead to the utter destruction of a dwarf galaxy. Overwhelming tidal forces can completely strip away all of its stars and gas, which are then absorbed into the fabric of the larger galaxy. This process of consumption is what creates the vast stellar streams we observe circling the Milky Way and Andromeda, providing us with a fossil record of past galactic mergers, and confirming that dwarf galaxies serve as essential building blocks that fuel the growth and chemical enrichment of their massive hosts. In some cases, these gravitational interactions lead to the utter destruction of a dwarf galaxy. Overwhelming tidal forces can completely strip away all of its stars and gas, which are then absorbed into the fabric of the larger galaxy. This process of consumption is what creates the vast stellar streams we observe circling the Milky Way and Andromeda, providing us with a fossil record of past galactic mergers, and confirming that dwarf galaxies serve as essential building blocks that fuel the growth and chemical enrichment of their massive hosts. In some cases, these gravitational interactions lead to the utter destruction of a dwarf galaxy. Overwhelming tidal forces can completely strip away all of its stars and gas, which are then absorbed into the fabric of the larger galaxy. This process of consumption is what creates the vast stellar streams we observe circling the Milky Way and Andromeda, providing us with a fossil record of past galactic mergers, and confirming that dwarf galaxies serve as essential building blocks that fuel the growth and chemical enrichment of their massive hosts. Another crucial factor in these interactions involves gas dynamics. As a dwarf galaxy plows through the superheated gaseous halo surrounding a larger galaxy, it confronts what is known as ram pressure. This force can effectively blow the gas out of the smaller system, which in turn halts star formation and prematurely ages the dwarf galaxy. This mechanism is particularly devastating for dwarf irregular galaxies, which rely on their gas reservoirs to continue creating new stars. Data gathered from both space-based and ground observatories confirms that even minor gravitational encounters can leave lasting marks on the structure and motion of dwarf galaxies. Irregular patterns in their brightness, drawn-out stellar distributions, and unusual shifts in stellar velocities all serve as telltale signs of past collisions, close flybys, and the enduring influence of tidal forces. Dwarf galaxies also have a significant impact on the architecture of the local group. They function as valuable tracers for the distribution of both ordinary mass and dark matter, pointing to regions where gravity is most concentrated. By analyzing the orbits and dynamics of these dwarf satellites, astronomers can map out mass distribution, determine the gravitational reach of large galaxies, and forecast future collisions and mergers. Interestingly, the interaction between a dwarf galaxy and its massive neighbor can also spark fresh episodes of star formation. When tidal forces compress vast clouds of gas, the density increases to a point where it can trigger the birth of new stars. This demonstrates that interactions with large galaxies are not purely destructive. They can simultaneously reshape a galaxy's structure, while also invigorating its cycle of stellar life. Advanced research techniques, particularly the astrometric data from the Gaia mission, allow scientists to track the movements of dwarf galaxies with unprecedented precision. This information is vital for building accurate models of their orbits, calculating the tidal forces they endure, and determining which of these systems are destined to be consumed versus which will remain in stable, long-term orbits. To summarize, the interplay between dwarf and large galaxies is a highly complex, multifaceted process that encompasses gravitational tides, gas dynamics, morphological changes, and shifts in stellar populations. This dynamic is fundamental to the evolution of smaller galaxies and the assembly of structures like the local group, offering astronomers profound insights into how massive galaxies have grown and changed over cosmic history. Dwarf galaxies stand as some of the cosmos's most enigmatic objects, with their incredible abundance of dark matter being one of their most compelling traits. For certain dwarf galaxies, the mass of all their visible stars accounts for just a tiny percentage of the system's total mass. This characteristic turns them into unparalleled laboratories for investigating the true nature of dark matter and how it shapes the formation and evolution of galaxies. Dark matter is a mysterious, invisible substance that doesn't emit light or interact with any form of electromagnetic radiation. But its presence is revealed by its gravitational pull. It is precisely this gravitational effect on the motion of stars and gas that enables astronomers to confirm its existence. In dwarf galaxies, especially the type known as dwarf spheroidal galaxies, or DSPH, stars exhibit unusual dynamics. They move much faster than the visible matter would suggest, pointing to the overwhelming dominance of dark matter in these compact systems. Spectroscopy of individual stars provides a key method for gauging the amount of dark matter. By charting the velocities and movements of these stars within the galaxy, astronomers can map out the distribution of mass. This technique has revealed that in dwarf spheroidal galaxies, the mass of dark matter can be hundreds of times greater than the mass of visible stars, positioning these galaxies as critical testing grounds for various models and theories about dark matter. Dark matter's influence extends beyond stellar motion, playing a crucial role in the very formation of galaxies. During the early universe, minor gravitational wells formed by clumps of dark matter acted as cosmic nurseries where gas could gather and ignite the first generation of stars. Dwarf galaxies can be seen as surviving relics of these primordial structures, granting them historical importance for understanding how the large-scale structure of the cosmos came to be. Various models attempt to explain how dark matter is distributed within dwarf galaxies, with some theories postulating dense central cores and others suggesting more diffuse, extended halos. Observational evidence indicates that in the majority of dwarf spheroidal galaxies, the dark matter is spread out rather uniformly. This even distribution creates a stabilizing effect that helps shield these small galaxies from being torn apart by the tidal forces of their larger neighbors, explaining their ability to endure for billions of years while orbiting giants like the Milky Way or Andromeda. The quantity of dark matter present in a dwarf galaxy is intrinsically linked to its mass and physical form. Galaxies containing a higher concentration of dark matter tend to preserve a spherical shape, more effectively resist tidal deformations, and maintain their ancient stellar populations without significant disruption. In contrast, dwarf irregular galaxies where dark matter is not as prevalent are significantly more susceptible to gravitational interactions and the subsequent loss of their gas. Investigating these small galaxies offers a way to test our theories about the nature of dark matter. For example, observing the movements of stars within dwarf spheroidal galaxies allows scientists to set limits on the potential interactions between dark matter particles themselves and with ordinary matter. Such data is indispensable for Earth-based experiments designed to detect dark matter and for the validation of cosmological models. Dwarf galaxies also act as crucial indicators of the universe's history of structure formation. Their dynamics and arrangement in space shed light on how dark matter congregates in the local group, how gravitational clusters are formed, and how smaller systems impact the development of larger galaxies. Every dwarf galaxy provides a unique glimpse into the early cosmos, permitting us to trace processes that took place billions of years ago. Consequently, the dark matter in dwarf galaxies is not simply a contemporary astrophysical enigma. It is also a fundamental key to understanding how galaxies form, how they survive in orbit around massive systems, and the part that small galaxies play in the evolution of the universe. The amount of gas a dwarf galaxy holds is a critical element that dictates its capacity to create stars and evolve. Despite their small scale, these galaxies display an incredible variety of gas conditions, ranging from being almost entirely depleted of gas to possessing abundant reserves of both cold and hot gas. Dwarf spheroidal galaxies, or DSPH, are notable for being virtually devoid of gas. Their interstellar medium is exceptionally thin, which is the outcome of several combined factors. Intense star formation activity in their past exhausted gas supplies. Tidal interactions with larger galaxies stripped their gas away. And powerful stellar winds and supernova explosions dispersed any remaining gas clouds. Because of this, these galaxies today are composed almost exclusively of old stars, and the birth of new stellar generations is an exceedingly rare phenomenon. Dwarf irregular galaxies, or DIRR, on the other hand, represent the complete opposite end of this spectrum. Their interstellar medium is richly supplied with gas, which is present in both cold, dense states and more diffuse hot ones. The cold gas, which is mostly hydrogen, is the primary fuel for making stars. Within these galaxies you can find active star-forming regions where gas is compressed into dense clouds, initiating the birth of new stars. A process they can maintain over billions of years, thanks to their ability to hold on to these gas reserves. A galaxy's gas content is directly associated with its metallicity. Gas that has been through numerous cycles of star formation becomes enriched with heavy elements, released from supernova explosions and stellar winds. In dwarf irregular galaxies, evidence of this metal enrichment is observable, although it is less pronounced than in large spiral galaxies. This characteristic makes DIRR galaxies compelling subjects for the study of chemical evolution on small scales. The effect that a large galaxy has on the gas supply of its dwarf satellites becomes apparent through processes like ram pressure and tidal effects. As a dwarf galaxy moves through the hot gaseous halo of a major galaxy like the Milky Way or Andromeda, it feels a pressure that displaces its gas, quenches star formation, and steadily converts a gas-rich system into a gas-poor one. These transformative processes are most commonly seen in satellite galaxies that orbit closer to the center of their large host. The interstellar medium of dwarf galaxies also contains ionized, neutral, and molecular gas, and each one fulfills a distinct function. The presence of ionized gas points to young, massive stars that are emitting ultraviolet radiation, and ionizing the hydrogen around them. Neutral gas acts as the reservoir for future star formation, whereas molecular gas becomes concentrated in dense clouds, where new stars are directly formed. Observations of dwarf irregular galaxies highlight the dynamic interplay between gas and stellar winds. Massive stars and supernova explosions generate turbulent gas flows, which carve out bubbles and plumes that can eject gas from the galaxy's center, while also triggering its compression in nearby regions. This ongoing cycle facilitates the gradual redistribution of gas and sustains active star formation over billions of years. Interestingly, even in dwarf spheroidal galaxies, astronomers occasionally discover remnants of gas clouds. These can serve as the origin for periodic, though exceptionally rare and faint, bursts of star formation. Finding these clouds requires highly sensitive radio and infrared telescopes that allow astronomers to detect even minimal concentrations of hydrogen and molecules. The arrangement of gas in these systems can also tell a story of their past. Features such as tails, extended gas streams, asymmetrical distributions, and localized concentrations are all signs of previous tidal interactions, close encounters, and accretion events. Therefore, by studying this interstellar gas, we can reconstruct the dynamic and evolutionary history of these small cosmic systems. In essence, the gas content and the interstellar medium are not just the building blocks for future stars, but are also indicators of a dwarf galaxy's history of interactions, its internal dynamics, and its chemical evolution. Without gas, these small systems forfeit their ability to evolve, becoming old and faint relics, while the presence of gas is what maintains their vitality, their growth, and the diversity of their stellar populations. Supernovae and stellar winds stand as two of the most critical processes that sculpt this evolution, with supernovae being the cataclysmic explosions that mark the end of a massive star's life. In dwarf galaxies, which have relatively low gas mass and weak gravitational pull, the energy released by a supernova can forcefully eject vast quantities of gas from the galactic core. This expulsion results in the formation of voids, plumes, and expanding bubbles, and can effectively pause star formation for millions of years, leading to periods of calm between bursts of cosmic activity. Supernovae also serve a critical function by seeding the interstellar medium with heavy elements. These cosmic explosions scatter carbon, oxygen, iron, and other materials that are later incorporated into new generations of stars and planets. This enrichment process is especially impactful in small dwarf galaxies, which may only contain hundreds of thousands or millions of stars, as it fundamentally shapes the chemical makeup of future stellar generations and defines the system's overall metallicity. Stellar winds, in contrast to the explosive nature of supernovae, exert their influence more steadily over time. Powerful streams of charged particles and energy flow from massive, hot stars, applying constant pressure to the surrounding gas. Within dwarf irregular galaxies, these winds stir up turbulence, compressing gas clouds in certain areas while dispersing them in others, which in turn creates localized pockets of vigorous star formation and preserves the dynamic complexity of the interstellar medium. The interaction between gas and the energy from both supernovae and stellar winds produces observable phenomena, such as immense bubbles and plumes of gas that are detectable in infrared and radio wavelengths. In dwarf galaxies, these features can take up a substantial portion of the galaxy's volume, resulting in asymmetrical and stretched-out shapes, particularly if the galaxy is in orbit around a much larger neighbor. Such elongated gas tails serve as clear evidence of past energetic outflows and tidal forces at play. The combined energy from supernovae and stellar winds also fuels the expulsion of gas from dwarf galaxies into the void of intergalactic space. This phenomenon, known as a galactic wind, depletes the galaxy's gas supply and puts the brakes on subsequent star formation. In dwarf spheroidal galaxies, this process can be so thorough that it removes all gas reserves, leaving behind a population composed entirely of ancient stars, while the effect is less severe in dwarf irregulars, whose greater mass and gravity help them retain some of their gas. Observations have confirmed a direct link between the energy output from supernovae and a galaxy's history of star formation. Galaxies experiencing vibrant bursts of new star creation also show a high rate of supernovae, which establishes a cycle of gas redistribution, compression, and renewed starbirth. This self-regulating cycle imposes a distinct rhythm on the life of a dwarf galaxy, characterized by an alternation between intense star-forming periods and quieter phases of gas reprocessing. You can also see how these energy outbursts influence the structure of dark matter, as they can shift not only gas but also some stars, leading to temporary imbalances that help us understand mass distribution and the interplay between visible and dark matter. Ultimately, supernovae and stellar winds are the main drivers regulating the dynamics, chemical composition, and evolutionary path of dwarf galaxies. They mold the interstellar medium, set the pace of star formation, affect the structure and retention of gas, and leave behind the visible signatures that we can observe today. Despite their modest size and limited resources, dwarf galaxies host an incredible variety of stellar populations, and by studying these stars, we can piece together the history of how these galaxies formed. The most ancient stars found in dwarf galaxies, with ages approaching 12 to 15 billion years, act as direct witnesses to the earliest epochs of the universe's history. Within dwarf spheroidal galaxies, these old stars constitute the vast majority of the population, because these systems ceased forming stars long ago and are now almost completely barren of gas. By analyzing the light spectra from these stars, astronomers can determine their chemical composition and metallicity, which provides clues about the number of star formation cycles and supernova events that have transpired. In dwarf irregular galaxies, you find a more complex and diverse age distribution among the stars. These systems feature both ancient populations that formed in the early cosmos and young stars that are currently being born within dense gas clouds. The age gap between different stellar groups allows us to reconstruct the galaxy's history of activity, pointing to times of prolific star birth interspersed with periods of relative quiet. The distribution of stars by mass is also a crucial piece of the puzzle, as these galaxies contain everything from massive, short-lived stars destined to become supernovae, to low-mass, long-lived stars that endure for billions of years. The metallicity of stars, which is their concentration of elements heavier than hydrogen and helium, is particularly telling. Old stars in dwarf spheroidal galaxies exhibit low metallicity, which suggests they formed under the primordial conditions of the early universe, when heavy elements were still rare. In contrast, dwarf irregular galaxies display a much broader spectrum of metallicity, as their younger stars are enriched with elements blasted out by prior generations of supernovae, reflecting the ongoing chemical evolution of the system. You can also observe a clear spatial arrangement of stars according to their age and mass. In dwarf spheroidal galaxies, the older stars tend to cluster at the center, creating a dense core, while the outer regions are populated more sparsely. Conversely, in dwarf irregular galaxies, young stars are concentrated in regions rich with dense gas, while the older stars are scattered more evenly throughout the galaxy's volume, illustrating how a galaxy's structure is shaped by star formation, turbulence, and external forces. One particularly fascinating aspect of dwarf galaxies is the presence of star clusters and associations. If you look at dwarf irregular systems, you'll find that open clusters of young stars generate localized pockets of intense brightness, which act as clear signals of recent star-forming events and give astronomers a way to evaluate the galaxy's current activity. In contrast, dwarf spheroidal galaxies are nearly devoid of such clusters, suggesting that their active phase of star formation has already concluded. Therefore, when you analyze the stellar populations within dwarf galaxies, you are not only able to determine the age and makeup of these diminutive systems, but also to grasp the dynamics of their evolution. This study reveals their history of chemical enrichment, their interactions with neighboring galaxies, and even the pervasive influence of dark matter. Stars essentially serve as living records of every process that has unfolded in these galaxies over billions of years. And by examining their characteristics, we unlock the secrets of how the universe's structure came to be. You'll find that dwarf galaxies very seldom exist in total isolation. The vast majority of them function as satellites, orbiting more massive galaxies, such as our own Milky Way or the Andromeda Galaxy. The interaction with these cosmic giants exerts a definitive impact on the structure, dynamics, gas content, and stellar populations of these smaller dwarf systems. Among the most crucial processes at play are tidal stripping and the tidal forces that arise from the gravitational influence of a large galaxy on its satellite. These forces have the power to draw stars and gas out of a dwarf galaxy, shaping them into extended tails and asymmetrical patterns, and in some cases, causing complete structural disruption. You can see these effects in action, for instance, with the dwarf satellites of the Milky Way, like Sagittarius or the Large Magellanic Cloud, where long trails of gas and stars serve as evidence of their past interactions. Tidal forces are also instrumental in stripping gas away from dwarf galaxies. Gas clouds, which are not held in place by sufficiently powerful gravity, can be ejected into the void of intergalactic space, which leads to a progressive loss of the ability to form new stars. You can observe this effect most clearly in dwarf spheroidal galaxies, which possess low mass and therefore have a weak gravitational grip. Over time, these galaxies are transformed into old, dim systems with almost no star formation activity. Furthermore, large galaxies can induce periodic tidal effects, a phenomenon that becomes especially pronounced if the satellite's orbit is highly elongated. During its closest approaches, a dwarf galaxy endures a sudden surge in tidal forces, which leads to the compression and heating of its gas as well as the redistribution of its stars. These powerful effects can stimulate localized bursts of star formation and give rise to distinct structural features such as rings, elongated central cores, and disk-like components. The influence of a large galaxy also makes itself known through the ram pressure exerted by the halo of hot gas that envelops the giant system. As a dwarf galaxy travels through this halo, gas from its own interstellar medium can be stripped away, in a process much like an object being buffeted by a strong wind. This mechanism, which we call ram pressure stripping, is a significant factor in the evolution of gas-rich dwarf irregular galaxies, systematically converting them into gas-poor systems. Another compelling aspect is how tidal forces impact the dark matter within dwarf galaxies. Research indicates that powerful tidal interactions can actually redistribute this dark matter, forging elongated structures, clumps, and temporary asymmetries. This provides astronomers like me with valuable information about how these small systems react to external gravitational disturbances, and reveals more about the intricate connection between their visible and dark matter components. A dwarf galaxy that undergoes the prolonged influence of a larger neighbor may experience what we call a morphological transformation. For instance, dwarf irregular galaxies subjected to long-term tidal forces and gas loss can slowly evolve into spheroidal systems that are entirely devoid of star-forming activity. This evolutionary path is one of the potential explanations for the variety of morphological types you see among small systems, and serves as a clear demonstration of how a galaxy's environment shapes its development. Ultimately, these interactions with a large galaxy leave behind observable clues that astronomers use to piece together the history of these small systems. Extended tails, lopsided star distributions, localized gas clusters, and variations in chemical composition all bear witness to past encounters and help us reconstruct the dynamic history of dwarf satellites. It becomes clear that tidal forces, ram pressure, and periodic interactions are the determining factors in the fate of these small systems, making them perfect subjects for studying gravitational evolution and galactic interactions. Now, despite their unassuming size and mass, dwarf galaxies are home to complex physical processes, which include the presence of magnetic fields and cosmic rays. You'll find these components play an essential part in the dynamics of interstellar gas, the processes of star formation, and the maintenance of internal turbulence within the galaxy. The magnetic fields in dwarf galaxies are generated through a combination of differential rotation, turbulent gas flows, and the lingering effects of past supernova explosions. While these fields are weaker than what you would find in large spiral galaxies, their effect on the interstellar medium is nonetheless substantial. They provide resistance against the compression of gas clouds, help regulate the flow of ions, assist in the propagation of cosmic rays, and influence the distribution of turbulent energy. Cosmic rays consist of high-energy particles, mostly protons and the nuclei of heavy elements, that have been accelerated in shock fronts, supernovae, and active star-forming regions. Within the limited gas volume of dwarf galaxies, these cosmic rays can carry energy over great distances, which helps to sustain turbulence and generate a pressure that directly affects the movement of gas. The interplay between magnetic fields and cosmic rays establishes a kind of self-perpetuating cycle. As cosmic rays travel along the magnetic field lines, they heat the surrounding gas, inflate bubbles, and create local pressure zones that feed into the galaxy's turbulence. This turbulence, in turn, fuels the dynamo process, which strengthens and preserves the structure of the magnetic field. My research suggests that these magnetic fields can ultimately stabilize the interstellar gas, preventing its premature collapse under the force of gravity. Within dwarf irregular galaxies, regulating local star formation is a critical process, especially since their weak gravity leaves gas highly susceptible to rapid dispersal. Magnetic pressure provides a crucial stabilizing force, helping to preserve gas clouds for millions of years. This containment creates the necessary conditions for a more gradual and consistent pace of star creation, preventing the galaxy from exhausting its fuel too quickly. Cosmic rays are also instrumental in distributing chemically enriched material across the galaxy. When a supernova explodes, it accelerates particles that then engage with magnetic fields, generating powerful flows. These currents scatter gas clouds and transport heavy metal elements to different galactic regions, a process that ultimately influences the metallicity of new stars and shapes the chemical landscape of these small systems. Furthermore, both magnetic fields and cosmic rays sculpt the very structure of these galaxies. They are responsible for forming elongated streams of gas, vast plumes, and localized bubbles, all of which are particularly prominent in dwarf irregular galaxies. Astronomers can observe these features across radio and infrared wavelengths, as well as through light polarization, which allows them to map the distribution of galactic energy and magnetic fields. It is crucial to recognize that interactions with larger galaxies significantly amplify these effects. The tidal forces, gas compression, and the journey of a dwarf galaxy through the hot halo of a massive neighbor all combine to increase turbulence. This heightened activity strengthens the internal dynamo process and boosts cosmic ray production, demonstrating how the external environment has a direct impact on the internal dynamics of these smaller systems. This interplay of factors directly governs the rate and intensity at which new stars are born. By creating zones of higher or lower pressure, magnetic fields and cosmic rays lead to uneven star formation across the galaxy. The outcome is a pattern of localized stellar bursts followed by extended periods of calm, which defines the cycles of activity commonly observed in dwarf galaxies. In essence, magnetic fields and cosmic rays are integral to the physical dynamics of dwarf galaxies, as they control turbulence, gas distribution, chemical enrichment, and star formation, thereby defining the distinct structures and life cycles of these small cosmic islands. Consequently, these galaxies serve as exceptional laboratories for investigating dark matter, offering profound insights into how this mysterious substance contains gas and stars and steers the evolution of small systems. Despite having very little visible mass, a great number of dwarf galaxies display an exceptionally high mass-to-light ratio, which points to the overwhelming presence of dark matter. This unseen component of the cosmos does not interact with light, but applies a powerful gravitational pull on all visible matter. In dwarf galaxies, this gravitational influence is especially pronounced, as the observable mass of stars and gas is nowhere near enough to account for their observed dynamics. By carefully measuring the speed and movement of stars within dwarf galaxies, astronomers can calculate the distribution of dark matter and map its density. These observations consistently reveal the existence of a massive and invisible dark matter halo enveloping the galaxy. This method allows us to perceive the otherwise imperceptible, confirming dark matter's foundational role in these structures. One of the defining characteristics of dwarf spheroidal galaxies, or DSPH, is their profound reliance on dark matter for their very existence. Spectroscopic analysis often shows that stars in these galaxies are moving at speeds far greater than their visible mass could sustain. This suggests a dense halo of dark matter is gravitationally binding the stars, preventing them from being torn apart by the pull of larger galactic neighbors. Dark matter is also vital for the retention of gas, particularly in dwarf irregular galaxies where star formation is ongoing and the mass of gas often surpasses that of the stars. Without the gravitational anchor of a dark matter halo, these essential gas clouds would be easily stripped away by tidal forces or blown out by supernova winds. But with it, star formation can persist for billions of years. The arrangement of dark matter within dwarf galaxies presents some unique features. Research indicates that the central areas of many dwarf spheroidal galaxies possess a flat density profile, which contrasts with the sharp, cuspy profile typically observed in larger, spiral galaxies. This discrepancy is thought to be a potential consequence of the complex interactions among stars, gas, and dark matter, possibly modified by tidal forces from neighboring galaxies. Moreover, dark matter significantly shapes the morphology of dwarf galaxies. The gravitational halo stabilizes their overall structure, protecting them from disruption during close encounters with other galaxies. This stabilizing effect is why dwarf spheroidal galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core and a relatively symmetrical form, while dwarf irregular galaxies can preserve a compact core. Dwarf galaxies are fascinating because they function as essential proving grounds for our models of dark matter. Their high concentration of this substance allows astronomers to rigorously test various hypotheses, including theories about cold dark matter and self-interacting dark matter, which seek to explain the structure and evolution of these small systems. Dark matter's influence is also evident in the orbital behavior of these satellite galaxies. When orbiting a larger galaxy, a dwarf galaxy's stable trajectory is a clear sign of a powerful gravitational shield, which can only be provided by a massive halo. Lacking this dark matter, many would quickly be disintegrated by tidal forces. Internally, dark matter also dictates the kinematics of stars, which move within the gravitational potential created by the halo, producing distinctive velocity profiles. Analyzing these stellar motions not only helps in estimating a galaxy's total mass, but also enables the study of dark matter distribution on small scales, a key focus in modern astrophysics. Dark matter is, therefore, a fundamental building block of dwarf galaxies. It binds stars and gas, stabilizes structures, governs orbits, and provides a crucial test for our physical models of the universe. Rich in this enigmatic substance, dwarf galaxies remain unparalleled objects for studying the invisible material that sculpts the entire cosmic web. You might be surprised to learn how susceptible dwarf galaxies are to powerful events, both from within and from outside, such as supernova explosions and the generation of galactic winds. These processes are absolutely essential because they govern how gas is removed, how chemical elements are spread around, and how the rate of star formation is controlled. When massive stars reach the end of their lives, they detonate as supernovae, and I find that in a dwarf galaxy, the energy from just one of these explosions can have a tremendous effect on the surrounding interstellar gas. The resulting shock waves stir up turbulence and can carve out vast, empty bubbles. And if you have many supernovae occurring together, their combined force can create a galactic wind powerful enough to eject gas from the galaxy itself. These galactic winds are incredibly efficient in smaller systems, primarily because the galaxy's own gravitational pull is too weak to hold on to the accelerated gas. This ejected material, which is the fuel for new stars, can be lost entirely, which helps us understand why you so often see dwarf spheroidal galaxies that are almost completely devoid of gas and composed mostly of ancient stars. However, it's not purely a destructive process. These galactic winds also serve a creative purpose. As they travel, they distribute the chemical elements forged inside supernovae across the galaxy and even into the void of intergalactic space. This ensures that new generations of stars are born with a richer mix of elements, which in turn influences their temperature, brightness, and overall evolution, allowing these tiny galaxies to maintain a surprising level of chemical complexity. Supernova activity can also directly trigger the birth of new stars by compressing interstellar gas into denser regions where formation can kick off. In dwarf irregular galaxies, this process results in their distinctive appearance, which you can see in their telltale clusters of young stars and irregular structures. This entire dynamic is made even more complex by the interplay between supernova energy, magnetic fields, and cosmic rays. Interestingly, all of this contributes to a natural self-regulation cycle for star formation. If you have too much star birth at once, you get a wave of supernovae that blows away the gas, temporarily shutting down any further star creation. Over time, as that gas cools and clumps together again, the cycle can begin anew, allowing these small galaxies to sustain a relatively steady level of activity over billions of years. When we look at dwarf galaxies across different wavelengths, we find direct evidence of this activity. Observations in X-ray and radio light show us the signatures of hot gas and expanding bubbles left behind by supernova-driven winds. These clues allow astronomers like me to piece together the history of a galaxy's stellar activity and gauge the true impact of these winds on its development. It's also important to realize that dwarf galaxies rarely live in total isolation. Their evolution and physical traits are profoundly shaped by their cosmic surroundings, from the density of the intergalactic medium to the presence of massive neighboring galaxies. This intergalactic medium is an incredibly thin plasma, and as a dwarf galaxy travels through it, it encounters a kind of cosmic headwind or ram pressure that can effectively strip away its gas. In particular, dwarf galaxies known as dwarf spheroidals, or DSPHS, are heavily impacted by the gravitational pull of larger galactic neighbors. These tidal forces can stretch and distort the smaller galaxy, pulling away both its gas and its stars. This process explains why these systems are often left with only their oldest stellar populations after a close pass with a giant like our own Milky Way. Conversely, you can see a different outcome with dwarf irregular galaxies, or DIRRS, which still contain gas. These systems can actually pull in and absorb gas from the intergalactic medium, replenishing their reserves and fueling ongoing star formation. The interaction is complex, as the gravitational influence from nearby galaxies can also trigger localized bursts of starbirth, while the dwarf galaxy's own dark matter halo provides a crucial gravitational anchor, helping it resist being completely torn apart by these external forces. When a massive galaxy draws near, it squeezes the gas within a neighboring dwarf galaxy, creating dense pockets that ignite a new wave of star formation. You can see direct evidence of this phenomenon in dwarf irregular galaxies, where you'll find clusters of young stars interconnected by luminous chains and arcs. This illustrates how the cosmic environment and the intergalactic medium are pivotal in shaping the destiny of these smaller galaxies, influencing everything from their gas supply and star-forming activity to their physical structure and chemical makeup. Gas accretion is the essential lifeline for dwarf galaxies, especially for gas-rich dwarf irregulars, also known as DIRR galaxies. They constantly interact with the intergalactic medium, pulling in gas that becomes the fuel for future generations of stars. This process is absolutely critical because their own gas supplies are finite and can be easily stripped away by internal forces like stellar winds and supernova explosions. Without this steady influx from the outside, star formation would eventually flicker out, leaving behind an old, gas-depleted system. Galaxies acquire this gas through several distinct mechanisms. One method is diffuse accretion, a slow and steady process where gas from the intergalactic medium is gradually drawn into the galaxy's gravitational halo over billions of years. A more direct route involves streams of cold gas flowing along the filaments of the cosmic web, creating narrow channels that deliver fresh hydrogen and trigger localized bursts of star formation. Furthermore, a dwarf galaxy can capture gas stripped from other systems during tidal encounters, a process that creates distinct features like gas tails and arcs, while causing a temporary surge in star-making activity. This process of gas accretion has a profound impact on the metallicity of the stellar population. Since the incoming intergalactic gas typically has a low concentration of heavy elements, it dilutes the more enriched gas already inside the galaxy, meaning new stars can form with lower metallicity than older ones. This influx also shapes the galaxy's physical appearance, supporting the disk-like or asymmetrical structures you see in DIRR galaxies, along with their characteristic chains and clusters of young stars. Scientific models reveal that the rate of gas accretion is determined by the galaxy's halo mass, its velocity, and the density of its local environment. For instance, smaller dwarf galaxies moving quickly through a hot intergalactic halo might lose gas faster than they can collect it. In contrast, more massive systems can successfully retain and accumulate new gas, which sustains their activity over long periods. Radio telescope observations support these models, showing vast clouds of hydrogen surrounding dwarf galaxies, which serve as reservoirs for future star formation and prove this cosmic interplay has been unfolding for billions of years. All of these complex interactions make dwarf galaxies exceptional laboratories for investigating star formation and the chemical evolution of smaller systems. The populations of stars you find within them vary dramatically based on their morphological type and their history of cosmic encounters. The most significant distinction lies between dwarf spheroidal galaxies, or DSPH, and their dwarf irregular, or DIRR counterparts, each telling a very different story of its life in the universe. Within dwarf spheroidal galaxies, you will find that the vast majority of stars are ancient, with ages ranging from 8 to 13 billion years. These stars were born in the early universe and have a low metallicity, which tells us that active star formation and chemical enrichment ceased very early in the galaxy's history. Conversely, dwarf irregular galaxies contain a vibrant mix of both old and young stars, with the younger generations forming from freshly accreted gas, indicating a continuous, if somewhat erratic, cycle of star birth. This contrast extends to the metallicity of their stellar populations. Stars with a low heavy element content dominate in DSPH galaxies, whereas DIRR galaxies exhibit a broad spectrum of metallicities, from ancient, metal-poor stars to younger generations formed from more enriched gas. It's also clear that the distribution of these stars is rarely uniform. Central regions often host younger, more metal-rich stars, while older, metal-poor populations are typically found in the outskirts, a layout that reflects the galaxy's gravitational history. Finally, the stellar populations you observe are a direct reflection of external influences. A close approach to a much larger galaxy can trigger tidal interactions and galactic winds that strip away gas, effectively halting star formation in its tracks. This process often leaves behind a dense, concentrated core of old stars, serving as a clear record of the powerful and transformative forces at play in a galaxy's cosmic neighborhood. In some instances, the outer regions of these galaxies can be quite sparse, featuring leftover young stars if the galaxy has managed to hold on to or pull in some gas. To describe the luminosity and the arrangement of stars in dwarf galaxies, astronomers often rely on models based on spherical symmetry or exponential distribution. You'll find that in dwarf spheroidal or DSPH galaxies, the star density plummets sharply as you move away from the center, whereas dwarf irregulars or DIRR galaxies show a much more scattered and asymmetrical layout tied to pockets of star birth and uneven gas clouds. The populations of stars within these galaxies serve as a remarkable chronicle of their interactions with cosmic neighbors. When you observe evidence of tidal tails, broken-up clusters, or lopsided stellar arrangements, you are seeing the fossil record of past encounters and mergers. These events heavily shaped the galaxy's gas reserves and its capacity for star formation, and by pairing chemical analysis with the age of these stars, we can piece together the unique life story of each dwarf galaxy. Ultimately, the stellar profiles you see in dwarf galaxies are a product of both internal dynamics, like star formation and supernova blasts, and external pressures, such as gas accretion, galactic winds, and tidal tugs from other galaxies. This wealth of information helps us grasp the evolution of these smaller systems and understand their contribution to the structure and chemical makeup of the wider universe. Despite their small stature and low mass, dwarf galaxies display a dynamic complexity that is truly astonishing. We measure the kinematics, or the motion of stars, within dwarf galaxies by using spectroscopic observations to determine the radial velocities of individual stars. With this data, it's possible for us to map out rotation curves and approximate the distribution of mass inside the galaxy. For dwarf spheroidal galaxies, The rotation curves are typically flat or rise very gently, which strongly suggests the overwhelming presence of dark matter holding the entire system together and preventing it from flying apart. When you look at dwarf irregular galaxies, their rotation curves present more defined characteristics. In these systems, both gas and young stars orbit a central point, which creates kinematics resembling a disk. However, this motion is frequently asymmetrical due to localized bursts of star formation, turbulent gas, and the gravitational influence of nearby galaxies. The role that dark matter plays in dwarf galaxies simply cannot be overstated, as its mass can be tens of times greater than all the visible matter combined. This dark matter halo is what guarantees the stability of the entire system, keeping its stars from dispersing and retaining its gas. If you were to remove the dark matter, most dwarf galaxies would quickly disintegrate due to internal pressures and external tidal forces. Kinematic analyses reveal that while stellar velocities in DSPH galaxies are generally low, variations in these speeds point to an uneven mass distribution and the potential for hidden substructures within the galaxy. In certain cases, you can even observe the lingering signs of past collisions, such as tidal tails, elongated forms, and skewed velocity patterns, which assist us in reconstructing the galaxy's orbital path and history. The dynamics of gas in dear galaxies are even more intricate, as the disk's rotation can be disrupted by intense episodes of star formation, winds from supernovae, and the infall of intergalactic gas, creating turbulent regions that make a straightforward dynamic analysis much more difficult. Studying these kinematics is also vital for estimating a galaxy's mass and mapping its dark matter distribution. By measuring the velocities of stars and gas, astronomers can construct models of the gravitational potential and gauge the concentration of dark matter. In DSPH galaxies, this concentration is frequently high, making them perfect laboratories for you to test theories of cold dark matter. The gravitational influence of the surrounding environment is also a major factor, as a close pass by a larger galaxy can trigger tidal effects that amplify internal turbulence and warp the distribution of velocities. Such powerful interactions can sometimes lead to a complete overhaul of the galaxy's dynamics, resulting in the formation of stretched or fragmented structures. Ultimately, the kinematics of dwarf galaxies help us comprehend the mechanisms that allow these small systems to remain stable. In DSPH galaxies, the stars move in a chaotic, random fashion, with very little organized rotation, making the galaxy dynamically hot. Conversely, the disk systems in DIRR galaxies display a hybrid nature, combining significant rotation with pockets of local turbulence, reflecting a delicate balance between internal and external forces that has shaped them over billions of years. By examining the dynamics and kinematics of dwarf galaxies, we can figure out how these small systems maintain their stability, interact with their surroundings, and evolve under the influence of dark matter. This information is the key to unlocking their evolutionary past and forecasting their future. Dwarf galaxies are also fundamentally important to the evolution of larger galactic structures like our own Milky Way, primarily through a process of absorption known as a merger or satellite accretion. Large galaxies, with their immense gravitational pull, steadily draw in these smaller systems, disrupting their forms and assimilating their stars, gas, and dark matter into their own structure. This cosmic consumption is a standard feature of galactic evolution and is crucial for the growth and structural development of massive galaxies. Near these larger systems, Tidal forces exert a tremendous and destructive influence on dwarf galaxies, as gravitational gradients stretch out their stars and gas into long, streaming tidal tails, effectively tearing apart their disks and spherical envelopes. At times, a dwarf galaxy can be completely dismantled, its constituent parts scattered throughout the halo of the larger galaxy, to create distinct stellar streams and fields of debris. These mergers and absorptions also lead to the chemical enrichment of the host galaxy. The infusion of young stars and gas with low metallicity from the dwarf galaxy mixes with the existing material, spurring the birth of a new generation of stars with an intermediate chemical composition, which over cosmic timescales contributes to greater chemical diversity within the stellar population. When you look at our Milky Way, you can see numerous stellar streams, which are essentially the ghostly remnants of dwarf galaxies that have been torn apart. By studying the distinct motions and chemical makeups of these streams, such as the well-known Sagittarius stream, we are able to piece together the history of our galaxy's mergers, revealing the timeline and sequence of how it consumed these smaller systems. It's important to understand that dwarf galaxies aren't always absorbed one by one. They can also be assimilated as part of larger groups. In these scenarios, several small systems interact with one another before they all merge with a much larger galaxy. This cascading process results in highly complex dynamic structures, including vast halos of satellite galaxies, arcs, and shells, which we observe both within our own local group and in distant systems where massive elliptical galaxies are still growing by feeding on their smaller neighbors. Computer simulations of these cosmic collisions demonstrate that dwarf galaxies possessing high velocities and dense central structures can actually withstand these interactions to a degree. They often manage to retain their core and a portion of their gas content, while the remainder of their mass is dispersed into the halo of the larger galaxy, creating intricate substructures. In contrast, lighter and more diffuse dwarf galaxies tend to disintegrate entirely, leaving behind nothing more than these faint, elongated stellar streams. Interestingly, the process of absorbing a dwarf galaxy can ignite fresh waves of star formation within the larger host. The gas delivered by the smaller system gets compressed by powerful tidal forces and mixes with the existing gas, which in turn triggers localized bursts of star creation. In certain situations, this can even lead to the formation of new compact disk structures or star clusters located in the outlying regions of the large galaxy. The influence of these small galaxies on the structural evolution of their massive counterparts is quite substantial. The accretion of these systems directly contributes to the growth of the halo, causes the primary disk to loosen or thicken, and introduces gravitational asymmetries. When combined with a galaxy's own internal dynamic mechanisms, these processes are what ultimately define the morphology and kinematic properties you see in large galaxies today. Within the dwarf galaxies themselves, active star formation plays a pivotal role in their evolution, structure, and chemical enrichment. These bursts of star birth are characterized by an incredible intensity, especially when considered relative to the system's small total mass. During these active periods, compact clusters of young stars are formed, which then aggressively interact with the surrounding gas through intense radiation, powerful stellar winds, and supernova explosions. These processes generate powerful outflows of gas, known as galactic winds, which are a key mechanism for regulating how dwarf galaxies evolve. The collective pressure from supernovae and intense ultraviolet radiation can accelerate gas to speeds exceeding the galaxy's escape velocity. This depletes the reservoir of available gas for future star formation, thereby limiting the galaxy's growth and causing it to enter periods of dormancy between its more active phases. Observations of dwarf irregular galaxies, or DIRR, reveal that these winds can sculpt asymmetrical features like arcs, bubbles, and localized voids within the gas distribution. In the more compact dwarf spheroidal galaxies, or DSPH, these galactic winds are often so effective that they lead to the almost complete removal of gas, leaving behind a system composed mainly of an old stellar population. Active star formation also profoundly impacts the chemical enrichment of dwarf galaxies. While supernovae enrich the nearby gas with heavy elements that can be used to form new generations of stars, the galactic winds carry some of this enriched material away. This process creates chemical gradients, where the central regions of the galaxy become richer in metals, while the periphery remains chemically less evolved. An intense burst of starbirth can actually create a self-regulating cycle. As gas is rapidly consumed and ejected, star formation slows to a crawl, allowing the galaxy time to reaccumulate gas, either from internal reservoirs or by accreting it from its surroundings. Once enough fuel is gathered, a new burst of activity becomes possible, establishing an irregular but recurring rhythm of star formation that defines the life of many small galaxies. Furthermore, these galactic winds have a direct effect on the galaxy's dynamics and overall shape. The removal of gas reduces the system's total mass, which alters the distribution of both stars and gas and can lead to structural elongation, or the formation of diffuse outer regions. These effects are especially pronounced in systems that are in close proximity to a large galaxy, where external tidal forces work to enhance the impact of the winds. Thus, you can see that active star formation and the resulting gas winds are the primary mechanisms that truly shape the evolution, structure, and chemical makeup of dwarf galaxies. They serve to regulate the rate of new star birth, create asymmetries in the distribution of gas, and enrich the system with heavy elements, playing a central role in the development of these small galactic systems. Dwarf galaxies, despite their modest mass, are deeply intertwined with the intergalactic environment that surrounds them. This intergalactic medium is composed of tenuous gas, stray particles, and the remnants of the cosmic microwave background radiation that permeates the space between galaxies. For small systems, these external conditions can have a major impact, particularly when a galaxy's trajectory takes it through dense clouds of gas, such as those within our local group, where a phenomenon known as ram pressure can strip away its interstellar matter. As a dwarf galaxy travels through the intergalactic medium, it encounters a force known as ram pressure, which acts upon its gas. This pressure can strip away gas from the galaxy's outer areas, depleting the reservoir of material needed for creating new stars. When you combine this effect with internal gas winds and tidal forces, it can trigger a significant drop in star-forming activity within these peripheral zones. The influence of the local group of galaxies, which includes our own Milky Way, is another critical factor. When dwarf galaxies exist as satellites to these much larger systems, they are subjected to immense tidal forces that can warp their structure and even pull away their stars and gas. These gravitational interactions are most pronounced in the outlying regions, where stars can be drawn into the gravitational field of the larger galaxy, eventually forming vast stellar streams and halos. At the same time, the accretion of gas from the intergalactic medium plays a vital, life-giving role. Small galaxies can pull in fresh supplies of gas from their cosmic surroundings, which can ignite new waves of star formation. Encounters with these cosmic gas streams can sometimes even set off localized bursts of activity, leading to the creation of compact clusters of young stars and shaping structural details like arcs and shells. Furthermore, the effects of the cosmic environment can be magnified by the presence of other nearby dwarf galaxies. A close flyby of a neighboring system can induce tidal disturbances, pulling out elongated structures and creating localized zones of turbulence. In certain situations, two dwarf galaxies might even partially merge before they are ultimately absorbed by a larger system, resulting in highly complex dynamic patterns. The chemical enrichment of a dwarf galaxy is also heavily dependent on its intergalactic environment. Gas that is accreted from outside the galaxy might be poor in heavy elements, which helps to establish chemical gradients within the system. Meanwhile, internal bursts of star formation and subsequent supernova winds work to redistribute metal-rich gas, generating variations in the chemical makeup of different stellar populations. Models of these interactions reveal that dwarf galaxies, situated within dense gas clouds, or as part of the local group, tends to evolve more rapidly, losing their gas, and bringing their star formation to an accelerated halt. In contrast, more isolated systems can hold onto their gas for much longer, which allows them to sustain their star-forming activity over many billions of years. Ultimately, a dwarf galaxy's evolution, its gas content, star formation rate, chemical composition, and structural development, is dictated by its intergalactic environment and local interactions. Even these very small systems are deeply intertwined with their cosmic surroundings, demonstrating that their destiny is inseparable from the larger galactic structures around them. Despite their modest size and mass, dwarf galaxies pass through incredibly complex and varied stages of evolution that span billions of years. This evolutionary path is shaped by a mixture of internal and external factors, from internal processes like star formation and supernovae, to external forces such as tidal interactions and the accretion of intergalactic gas. Dwarf galaxies can follow different evolutionary paths based on their initial conditions and the environment they inhabit. In the earliest phases of their existence, they emerge from clouds of cold gas that slowly contract under gravity, giving rise to the very first generations of stars. These pioneering stars live fast and die young, enriching the surrounding gas with heavy elements through supernova explosions, and thereby laying the essential chemical groundwork for all future generations of stars. The dynamics of this early evolution are frequently marked by intense bursts of star formation. These powerful episodes generate strong gas winds that can expel a portion of the interstellar material, which in turn can put the brakes on subsequent star formation. Consequently, the galaxy cycles through alternating phases of high activity and relative quiet, creating a structure that is irregular yet follows a recurring pattern. Over the vast expanse of cosmic time, dwarf galaxies inevitably feel the gravitational pull of their larger neighbors. A close approach to a massive galaxy initiates tidal interactions that can distort the dwarf system's structure, stretching its stellar components into long, graceful tidal tails. These partially shredded dwarf galaxies can then become the source of the stellar streams that we observe in the halos of large galaxies today. The ongoing influence of the intergalactic medium also profoundly affects their long-term evolution. While the accretion of gas from the surrounding cosmos can spark fresh waves of star formation and maintain the system's vitality, ram pressure can conversely strip that gas away, hindering the birth of new stars, especially in the galaxy's outer regions. The chemical evolution of dwarf galaxies is a gradual process. The initially low metallicity of the gas clouds increases over time through repeated cycles of star birth and supernova death. However, the loss of gas through stellar winds and interactions with neighboring galaxies creates distinct metallicity gradients and compositional inconsistencies. As a rule, the central areas become more enriched with heavy elements than the periphery, a difference that is reflected in the composition of stars from various generations. The cumulative effects of time and interaction are also clearly visible in the morphology of dwarf galaxies. Spheroidal systems tend to lose their gas over time and become static, dominated by ancient stellar populations, whereas irregular galaxies often manage to retain their gas and young stars, allowing them to form disk-like structures and localized star clusters. Modern observations reveal that many of the dwarf galaxies you see today are the product of numerous distinct evolutionary phases, including bursts of star formation, gas inflows and outflows, interactions with large galaxies, and internal dynamic processes. These stages collectively sculpt both the physical and chemical characteristics of the galaxies, making the history of each system truly unique. Therefore, the evolution of dwarf galaxies through time represents a delicate equilibrium between internal processes and external cosmic influences. These small systems, for all their modest size, play a crucial part in the formation and development of large galaxies, and by studying them, you and I can better comprehend the universal laws of cosmic evolution. Investigating dwarf galaxies requires a broad array of astronomical methods and instruments to gather data on their composition, structure, and dynamics, with spectroscopy being one of the principal techniques. Through spectral analysis, you can determine the chemical makeup of stars and gas inside dwarf galaxies, measure the velocities of their individual components, and even detect the movement of gas flows. Spectroscopy allows you to construct diagrams of velocity and metallicity, which are essential for piecing together the history of star formation and understanding how a galaxy interacts with its cosmic surroundings. Photometry offers you another critical set of tools, as it measures the brightness of stars and gas clouds across various ranges of light. With modern telescopes gathering data in the visible, infrared, and ultraviolet spectrums, you can study both ancient and newly formed stars, as well as pinpoint regions where star birth is actively occurring. To study the gas and dust within these systems, you turn to radio observations. Dwarf galaxies are frequently rich in neutral hydrogen, known as Hi, which emits radio waves at a distinct wavelength of 21 centimeters. These radio signals enable you to map the distribution of gas, measure its total mass and velocity, and identify streams of gas being expelled from the galaxy by stellar winds and tidal forces. Modern research into dwarf galaxies relies heavily on space telescopes like Hubble and James Webb, among other observatories. By operating beyond the distorting effects of Earth's atmosphere, these instruments provide you with images and spectra of unparalleled resolution. This clarity reveals fine structures that would otherwise be invisible, such as individual star clusters, expanding gas bubbles, and the faint halos surrounding these small galaxies. A crucial strategy in your study of dwarf galaxies is the combination of different methods. Spectroscopy gives you insight into composition and motion. Photometry uncovers the age and distribution of stars. And radio observations detail the structure of gas. Analyzing this data together allows you to create a complete and multifaceted picture of a galaxy and its evolution. To see how these methods are applied, you can look at the Sagittarius dwarf galaxy, located near our own Milky Way. The joint analysis of spectroscopic and photometric data has unveiled a complex history of mergers, revealing elongated stellar streams and an uneven distribution of heavy elements. Similar approaches are used to study other systems, like dwarf irregular galaxies, where you focus on active star formation and powerful gas flows. All of this observational data is fundamental to building modern models of dwarf galaxy evolution. The information you gather helps refine the initial conditions, wind speeds, and the effects of environmental pressures in these simulations. Each new observation allows you to adjust theoretical scenarios and deepen your understanding of the processes that govern the formation and development of small galaxies. Therefore, observational techniques, spectroscopy, photometry, radio astronomy, and space-based observation form the bedrock of your understanding of dwarf galaxies. These methods allow you to investigate their chemical composition, dynamics, structure, and evolutionary paths, uncovering the intricate interactions between these small systems, their environment, and larger galaxies. Dwarf galaxies assume a vital role in cosmic evolution, functioning as the primary building blocks for the assembly of larger galactic systems. According to contemporary cosmological models, massive galaxies like the Milky Way or Andromeda were formed through a gradual process of accreting and merging with these smaller stellar collections over billions of years. Due to their relatively low mass, dwarf galaxies are easily influenced by tidal forces and can be absorbed by their more massive neighbors. As this happens, they often leave behind stellar streams, thin, elongated trails of stars that you can observe today in the halos of large galaxies, serving as fossil records of these past mergers. The accretion of dwarf galaxies is also responsible for enriching the outer regions of large galaxies with heavy elements. The gas and stars from these smaller systems introduce new chemical components, including oxygen, carbon, and iron, which in turn influence subsequent waves of star formation in their new galactic home. When you observe our own local group, you can see that the Milky Way is enveloped by numerous dwarf satellite galaxies. Some, like the Sagittarius dwarf galaxy, are in the active process of being merged, creating complex stellar streams that alter the structure of our halo. Others, such as the Large Magellanic Cloud, continue to form stars and interact with the gas disks of larger galaxies, triggering localized bursts of new starbirth. The merger of small galaxies is a key factor in how large systems grow their mass. When a dwarf galaxy is absorbed, its stars are gradually integrated into the halo and disk of the larger galaxy, which changes its kinematics and can generate complex structural features. Some of these mergers can even induce disturbances that lead to the formation of spiral arms or trigger the development of bars in galactic disks. You can also see the long-term influence of dwarf galaxies on the dynamics of the halo. Even after being completely absorbed, their constituent stars continue to travel along elongated orbits, creating lasting asymmetries and structural variations. By conducting high-precision mapping of stellar velocities and chemical compositions, you can reconstruct the merger history of a large galaxy. Furthermore, dwarf galaxies act as natural laboratories that help you study the formation processes of much larger systems. Their relatively simple structures and sensitivity to external forces allow astronomers to model accretion, stellar winds, and tidal interactions with greater clarity, applying these models to understand more massive and complex galaxies. In essence, the role of dwarf galaxies in the formation of larger ones is to provide them with mass and to enrich them both chemically and dynamically. Through accretion, mergers, and the creation of stellar streams. These small systems become a fundamental part of the evolutionary story of our entire local group and beyond. Among the diverse types of dwarf galaxies, you can find systems with unusual characteristics that draw special attention from astronomers. One of the most intriguing varieties is the ultra-compact dwarf galaxy. These systems are set apart by their exceptionally high stellar density and compact size, making them unique objects for studying the extreme conditions of star formation and the dynamics of dense stellar populations. Ultra-compact dwarf galaxies frequently contain masses comparable to those of small star clusters, yet their physical size is much greater. This distinction presents you with a compelling puzzle concerning their origin and evolutionary history, prompting deeper questions about how such dense and unusual objects came to be. Certain theories lead me to believe that they might be the leftover cores of larger galaxies, which had their outer layers torn away by gravitational interactions. When you observe ultra-compact dwarf galaxies, you find they are defined by their incredibly high stellar density, small size, and minimal total mass, which makes them look like isolated islands of stars in the vastness of space. Despite their modest dimensions, these galaxies are home to a vast number of ancient stars, and their internal dynamics often point to the presence of dark matter, although its specific distribution is a topic I am still actively researching. Dwarf elliptical galaxies constitute another distinct classification of these cosmic structures. When you examine these systems, you'll see they have a spherical or slightly elongated form, exhibit very little star-forming activity, and typically hold a minimal amount of gas. Their star populations are quite old, and for their mass, they possess a relatively high concentration of heavier elements. You will often find dwarf elliptical galaxies within the halos of large galaxies and inside galaxy clusters, where powerful external tidal forces work to stabilize their structure and halt any further star formation. Dwarf irregular galaxies are small chaotic systems characterized by energetic star formation. They hold substantial reserves of gas and dust, and within them, you can often witness localized bursts of stellar creation. These galaxies are particularly compelling to me because their physical processes, such as internal stellar winds, churning gas flows, and tidal interactions, give you a clear, real-time demonstration of the dynamics at play within small cosmic systems. You can also find exceptionally rare subtypes, including dwarf spiral galaxies that have managed to preserve small disk structures and even faint spiral arms. Systems like these are exceedingly uncommon because small galaxies typically cannot sustain such delicate disks against the powerful tidal forces exerted by their larger cosmic neighbors. Studying these unusual and scarce systems helps astronomers like me appreciate the sheer diversity of evolutionary pathways available to dwarf galaxies. For example, I theorize that ultra-compact galaxies may be what's left of more massive systems that were stripped of most of their mass by gravitational interactions, whereas dwarf elliptical galaxies are often the final result of prolonged gas expulsion and the complete shutdown of star formation. My interest is particularly focused on the satellite halos of large galaxies, where you can find both old, metal-rich dwarf ellipticals and young, active dwarf irregulars. A careful analysis of these systems allows us to piece together the history of cosmic mergers and accretion, and to grasp how small galaxies shape the chemical composition and structure of their massive hosts. A significant part of this work also involves the investigation of dark matter in these small-scale systems. With their low mass and extreme sensitivity to external forces, Dwarf galaxies provide you with a unique opportunity to map the distribution of dark matter and to rigorously test our cosmological models. Some ultra-compact galaxies display perplexing rotation curves, which directly challenge our conventional understanding of how dark matter is arranged in such small environments. From this, you can see that these unusual and rare dwarf galaxies function as unique laboratories for studying cosmic evolution. They allow me to investigate the processes of star formation, interactions with larger galaxies, gas loss, and the influence of tides and dark matter. Ultimately, they offer a crucial key to understanding the incredible variety of galactic forms and structures you see across the cosmos. Stellar streams and the remnants of dwarf galaxies are remarkable cosmic structures that permit astronomers like me to literally read the history of galactic interactions and mergers. When a dwarf galaxy is subjected to the powerful tidal forces of a larger neighbor, it begins to gradually shed some of its stars. However, these stars don't just disappear. Instead, you can observe them forming enormous, stretched-out stellar streams that extend for tens and even hundreds of thousands of light years. Structures like these are direct evidence of recent or ongoing mergers between small systems and more massive galaxies. The Sagittarius stream, which wraps around our own Milky Way, is a classic illustration of this process. This particular dwarf galaxy is currently being torn apart and absorbed, leaving behind long tendrils of stars that you can observe with modern telescopes. By analyzing the velocities and chemical compositions of these stars, my colleagues and I can reconstruct the dwarf galaxy's trajectory and learn how it is slowly becoming part of the Milky Way. Stellar streams also give you a powerful method for uncovering the structure of dark matter within galactic halos. The density and shape of these streams are highly sensitive to the surrounding gravitational field, so by studying their deviations, we can draw conclusions about how this invisible mass is distributed. In this way, you can see that dwarf galaxies continue to act as markers of cosmic structure long after they have been destroyed. In addition to streams, you can sometimes observe the remnants of dwarf galaxies, compact cores or star clusters that have managed to survive tidal destruction. These leftovers can preserve a unique chemical makeup and stellar age, distinct from the surrounding halo, making them vital for my work in understanding the history of stellar populations and mergers. Modern observational programs, using data from space telescopes and wide-field ground-based observatories, allow us to create highly detailed maps of these stellar streams. This not only lets us track the paths of individual dwarf galaxies, but also helps you understand their influence on the formation of the spiral disks, halos, and bars of large galaxies. Furthermore, you'll find that stellar streams reveal a wide range of evolutionary scenarios. Some streams originate from dwarf galaxies that had active star formation and were rich in gas, thereby creating complex chemical patterns. Others are composed exclusively of old, metal-rich stars, which points to ancient systems that were destroyed long ago. An important aspect of this is how stellar streams and remnants help me test cosmological models, particularly the theories of hierarchical galaxy formation. By comparing the observed streams with the outcomes of computer simulations, you and I can verify the accuracy of our assumptions about merger rates, dark matter mass, and the duration of accretion events, making them far more than just beautiful cosmic phenomena. Dwarf galaxies serve as living testaments to the history of galactic mergers, interactions, and evolution, while also acting as a crucial instrument for investigating the structure and spread of dark matter within large cosmic systems. Throughout this lecture, we've explored their many facets, from their classification and role in the growth of major galaxies to their involvement in creating stellar streams and the distinct characteristics of ultra-compact, elliptical, and irregular types. These studies confirm that dwarf galaxies are not mere cosmic footnotes, but are, in fact, foundational elements of cosmic history. One of the most critical takeaways is that these smaller galaxies function as the primary building blocks for more massive systems. For billions of years, processes like mergers and accretion have sculpted the spiral and elliptical galaxies you see today, forming their halos and stellar streams while enriching them with heavy elements. Every interaction between a dwarf galaxy and its larger counterpart leaves behind a distinct signature, which we can observe in the form of these stellar trails and the remnants of consumed systems. Investigating dwarf galaxies also provides a powerful method for researching dark matter. Because the dynamics and stellar arrangements of these small systems are highly sensitive to the gravitational pull of their massive neighbors, their behavior allows us to deduce the mass and shape of the invisible matter composing the halos of large galaxies. This information is vital for testing cosmological models and fine-tuning the parameters of theories on how structures formed in the universe. The future of dwarf galaxy research is intrinsically linked to the progress of high-precision observational technologies and new space missions. Upcoming ground-based observatories and advanced space telescopes will empower us to discover previously unseen dwarf galaxies, monitor stellar streams in unprecedented detail, and analyze the chemical makeup of these small systems. Such advancements will create new avenues for studying the early universe, the dynamics of galactic halos, and the evolution of stellar populations. Researchers are particularly focused on rare and unusual dwarf galaxies, including ultra-compact and dwarf spiral systems. A thorough examination of these objects will deepen our comprehension of the extreme conditions under which small galaxies can exist, and the mechanisms that allow them to preserve their structure in stars against immense tidal forces. Furthermore, dwarf galaxies are essential for unraveling the chemical evolution of the cosmos, as their stars hold unique elemental signatures that point to early waves of star formation and the history of galactic interactions. In summary, dwarf galaxies may be small, but their importance in the cosmos is immense. They are instrumental in revealing the formation history of large galaxies, the architecture of dark matter, the chemical story of the universe, and the dynamics of gravitational interactions. Their study remains a cornerstone of modern astronomy, continuously pushing the boundaries of our understanding of the universe's structure and evolution.